Hello to everyone. I'm Alejandro Pérez Rodriguez from IREC, which is the Catalonia Institute for Energy Research in Barcelona, in Spain, where I head the photovoltaics group. And it's a big pleasure for me to chair this BIPV thematic session with the Sustainable Places virtual conference. So we are going to have this session is organized around the presentation of 8 ongoing European projects that are covering different relevant aspects related to BIPV that will allow us to have a very realistic diagnosis of which is the situation about research, technology, innovation, and development in these technologies, and which is the situation now. So this is organized in 3 topics. The first topic is how to trigger BIPV penetration in the building sector. The emphasis in this case is bringing down costs to allow these technologies to be more competitive. The first project will be the BIPV boost that will be presented by Jose Maria Vega de Seoane from Tecnalia. Here, the focus is bringing down the cost of multifunctional building integrated photovoltaic systems, limiting our costs with respect to traditional non-PV construction solutions, and includes an effective implementation of short and medium-term cost reduction roadmaps addressing the whole BIPV value chain and demonstration of the contribution of the technology towards mass realization of near-zero energy buildings. The second project in this first part of the session is Be Smart, that will be presented by Laura Manuel Perret from EPFL. Here, the focus is to break the multiple barriers which have been holding back the diffusion of BIPV by supporting industrialization of new materials and processes for the manufacturing of multifunctional BIPV elements, with a focus on breakthrough transformative approaches to realize in a cost-effective way aesthetical models. Aesthetics is also an important issue with BIPV, we will see, and also working at improved manufacturing processes, allowing the targeted cost reduction. Here also emphasis is to reduce production costs. And the last in this first part of the session is PV Adapt, that will be presented by Antonis Pepas from NTUA, from the National Technical University of Athens. Here, the emphasis of this project combines the concepts of modular construction and modular photovoltaics to develop adaptable and multifunctional building integrated photovoltaic systems with lower costs, development of flexible and low-cost production of PV systems in the automated process, and prefabrication will also be a key element in the case of this project. The second part is what we entitled Close to Market BIPV Solutions Demonstrated on Pilot Buildings in Europe. Here, the emphasis is the design, installation, and operation of BIPV demonstrator in pilot buildings as a way to enhance the penetration of BIPV solutions. Here we have 2 projects. PV sites will be presented by Eduardo Roman from Tecnalia. Here, the main objective is to drive BIPV technology to a large market deployment by demonstrating an ambitious portfolio of building integrated solar technologies and systems, giving a forceful, reliable answer to the market requirements identified by the industrial members of the consortium in their day-to-day activity. And the second project is Energy Matching, that will be presented by Laura Maturi from EURAC. This is maybe a more global approach. In this case, the project wants to maximize the renewable energy sources harvested in the built environment by developing and demonstrating cost-effective active building scheme solutions as part of an optimized building energy system. And they include also the connection of the system to the local energy grid and the management in a district energy hub, implementing optimized control strategies within a comprehensive economic rational balancing objectives and performance targets, including both private and public stakeholders. So in this case, for these 2 projects, emphasis, as I commented, is about the big demonstrators in pilot buildings. And the final part of the session will be devoted to, there are 3 projects that are devoted to next generation non-intrusive transparent BIPV solutions. In this case, we are dealing with BIPV elements that have an additional functionality, which is transparency. In fact, the three projects are dealing with the development and demonstration of solar windows, smart solar windows. And the idea is to develop a new generation of windows integrating also PV functionality. And they are including an additional issue is the non-intrusiveness. So what they propose is develop systems where the PV functionality has no visual impact and does not modify the aspect or the aesthetics of the window. So the user will not recognize that really this is a BIPV window, but this is like a standard window. There are three projects related to this topic, the ongoing projects. Tech for Wind and Impressive are projects that are dealing with a similar technological approach, even using a similar concept, even using different technologies. In both cases, the concept is to develop windows integrating tandem-like structures, combining ultraviolet selective solar cells with infrared selective solar cells. So this is the concept of wavelength selective solar cells, which means that are solar cells that absorb only a selective part of the radiation of the sun radiation. And the idea in this case is, by this way, is to have a very high level of transparency in the windows in this tandem-like device structure. In the case of Tech for Wind, we are using technologies based in the use of thin film oxides or thin film chalcogenide technologies for the ultraviolet selective cells and organic infrared selective devices for the infrared selective cells. While in the case of Impressive, the technologies include ultraviolet perovskite solar cells, wide bandgap perovskites as the ultraviolet selective solar cell, and near-infrared dye-sensitized solar cells for the infrared selective solar cell. Both Impressive and Tech for Wind are projects that are in a TRL level between 3 to 5. So it's our innovative projects with a strong level of innovation. On the other hand, it has Solar Wind. Solar Wind is a fast track to innovation action, which means that it is very close to the market. The idea, the objective in this case is to bring to the pre-commercial stage at TRL-A, very high TRL level, a patented solution to produce colorless and truly non-intrusive transparent BIPV windows in 2 years' time. And these are based in the concept of luminescent solar concentrator devices that are integrating customized thin film PV modules in the window frame. So this is the structure of the session. I think, I don't know if we are a bit ahead of time, maybe we can go to the first presentation related to the BIPV project.
Okay.
It's the PowerPoint is perfect. Yeah.
Okay. So I will proceed to the presentation. Thanks, Alejandro, for your kind introduction and to the organizers of Sustainable Places for inviting us. I am José Mari Vega Seoane from Tecnalia. I'm the coordinator of BIPV Boost, and I'm very glad to represent the consortium today. I will proceed to the contents because I've got, well, a quite loaded presentation, although I hope I can manage with the time I was given. So I will describe the project very briefly. I will explain the main objective and provide a global overview of what we are trying to implement in BIPV Boost. Then I will go into the details of some of the main results we have in each of the work packages of the project, and I will finalize with a brief reference to the next steps we are following. So concerning the project, it is framed in the topic related to the demonstration of significant cost reduction for building integrated PV solutions. It is coordinated by Tecnalia, and well, the consortium is built with 19 partners coming from 7 different countries. Well, it is an industry-driven project with some reference players in the BIPV field, such as Onyx Solar, Flisson. Then we have building skin developers with interesting products such as tulips, pits, Schweitzer, etc. And then on the research side, we have strong support from Subsea, URAC Research, CSTB also. So in general, we were trying to look for a consortium that covered the value chain as much as possible, and I think we succeeded in this regard. I moved to the objectives. I was hesitating when I was preparing the presentation whether I should present the typical list of specific objectives, and I finally decided that probably this slide well, was quite self-explanatory on what we are trying to do in BIPV Boost. So we are trying to move from the iconic and costly BIPV towards a mass market and cost-effective approach, allowing the real market implementation. So as we all know, BIPV was for the last decade at least always a hot topic, a market that was about to bloom, but at the end, well, the market didn't grow as expected. And so what we are trying to do with BIPV Boost is to really impact the market by reducing the extra cost of BIPV solutions as compared to reference and traditional construction products. So as I said, what we are trying to do is to reduce the extra cost of BIPV by 50%, as defined in the set plan for PV. And we are trying to do this by implementing a holistic cost reduction roadmap along the whole value chain, mainly grounded in 4 main pillars. On the one side, advanced manufacturing, by developing a flexible and automated BIPV manufacturing line that allows the manufacturing of customized BIPV solutions at a cost-effective, in a cost-effective way. Then also progressing in the cost reduction roadmap of very promising BIPV envelope solutions. Then also implementing a digitalization-based strategy along the value chain. And at last, progressing towards a BIPV-specific standardization framework. So this is basically the main pillars of our project. Then I provide here an overall structure of the project very briefly. So we have a first work package dedicated to the assessment of competitiveness and cost reduction roadmap for BIPV. This is one of the topics we are analyzing in the project, and I think this was done with a very high quality by CARES, Becquerel Institute. Then, as I mentioned, we have the manufacturing line development, cost reduction at module level and at building skin level, a work package dedicated to standardization of BIPV. Then 2 work packages focusing on digital and data-driven processes for BIPV cost reduction. On the one side, covering design to installation phases, and on the other hand, operation and maintenance issues. And then, of course, demonstration in real buildings and exploitation and dissemination communication activities. So I move to the results, starting with work package 1 on the roadmap for cost reduction. Well, we have already 2 public reports providing an extensive analysis and well, methodology for the assessment of competitiveness and cost reduction of BIPV. So these are reports are available in the website in the link you can see in the screen. I invite you to go and check and analyze it. analyze them in detail, since there are well, quite interesting conclusions we can draw from this analysis. And in the short term, we will also have 2 public reports on the BIPV potential assessment in the frame of near zero energy buildings, and the first LCA screening report of on BIPV. So very briefly, I wanted to comment on a few key takeaways from the competitiveness and cost reduction roadmap analysis from what conducted by Becquerel Institute. So there's still a very big dependence on the compensable retail electricity prices and supporting schemes. For example, in Belgium, green certificates, and in Italy, net billing. On the other hand, BIPV is already an attractive investment in all the locations that were studied in these reports, when roof systems are applied on residential housing. Then, concerning facade, well, facade systems are not competitive except for places where there are supporting schemes for PV in place, and or well, high or moderate irradiation levels, such as in Belgium, Italy, or Spain. Then an interesting point of view of this analysis is the sensitivity analysis, showing that the improvement of certain parameters have a significant impact on competitiveness. And I will explain very briefly. So, for example, a 10% increase in the relative increase of efficiency, combined with a 10% reduction on total end user cost, well, has an impact on the progress on competitiveness by 50%. So with a small improvement in certain parameters, we are able to deliver a great impact in the market. And this is something that well, BIPV Boost project is already doing, and hopefully we are well aligned with this strategy. And then, as a final conclusion on competitiveness, well, we can say that we are not far from the end user cost levels. So if technology develops and the market develops as planned, competitiveness should be reached by 2025 in most cases. So this is quite encouraging, I would say. Then moving to work package 2 on the manufacturing line of Mondragon Assembly. Well, here we are developing a completely flexible and automated BIPV manufacturing line that will allow the manufacturing of customized BIPV products using a different range of solar cells, different string length, cell distances, and positioning in the module. We are also introducing inline quality control solutions, and as a consequence, we aim that the manpower costs will be reduced by 50% and the scrap reduction by 80%. We are now about to well, install and commission the manufacturing line at Onyx, and in principle we expect that it will be operational in early December. At module level, well, Onyx is working on different topics. On the one side, new color technology for the rear glass of BIPV modules, then patterned amorphosilicon solutions, a walkable floor based on back contact solar cells, and also bifacial solutions for balustrade applications. And yeah, well, we are also working on the upscale of manufacturing processes to deliver Excel formats. And okay, on work package 4, we are developing 3 different building skin solutions. On the one side, we have a PITS product, which provides a multifunctional BIPV system that includes insulation. We are targeting a cost reduction of 30% at this product level by the end of 2020. Then we have the evolution of Tulip's click and go solution, which provides an easy installation solution. And they are providing a new design that leads to further cost reductions, and also working on the optimization of the gluing and assembly process with a target cost reduction of 50%. Then we have the partnership between Frisom and Schweitzer in the development of a new roofing kit, with also a strong cost reduction target of more than 50%. And then, as a proof of the scope of the project and how the value chain is represented in the whole action, we have a task dedicated to improving back-end logistics and the cost reduction, the cost reduction related to the BIPV module on transport and crating, which we are aiming to reduce by 57%. In work package 5, concerning standardization, the aim here is to move from the current EN 50583 standard to a BIPV specific and performance-based approach. So as you know, currently the qualification of BIPV solutions is fragmented, and we qualify on the one side PV related aspects, and on the other hand separately construction related issues. As I was pointing out in the slide, PV plus building is not equal to BIPV, and there are certain aspects that need to be addressed in a combined and simultaneous manner. So in the project, we are proposing a new approach in which we are developing new testing methodologies based on the current and existing standards, but adapting them to the reality of BIPV. And we are doing this in different topics: energy economy, mechanical safety, fire safety, and electrical safety in non-conventional scenarios. We have also a public report available in the website, which I also invite you to check. Then in work package 6 and 7 on digitalization, we have on the one hand BIM solar software, which is BIPV dedicated BIM-based software, and we are targeting in the project the transition from a bare software tool to a collaborative platform covering the whole value chain. We have so far developed the first prototype optimizing BIPV layouts at pre-design stage and considering costs and energy production. And then on the other hand, concerning BMS, we have also developed and analyzed a cost model parameterization for different use cases, and the first identification of required monitoring and control systems. And at last, also, we have developed a first prototype of BIPV digital twin, aimed at providing a generation forecasting tool to BMS and training datasets to failure detection and diagnosis. Then I move to demonstration activities. We have 4 demo sites, an office building in which we will demonstrate the bifacial balustrade and the walkable floor from Onyx. Then we have an industrial building where we will demonstrate a ventilated facade with also some shading potential, and Tulip's new lock and go installation system. Then we have a single family house where we will demonstrate the Frisom and Schweitzer roofing solution, and at last a multi-family house in which we will demonstrate the EPITS product. And finally, in work package 9, we have on the one side also public reports updating the market and stakeholder analysis and the regulatory framework of BIPV. And in terms of dissemination, I just wanted to mention some of the numbers we are observing in terms of interest from stakeholders, which are quite encouraging. 13,000 visits to the website, more than 7,200 downloads, on the public reports we have available on the website, and well, 8 articles presented in conferences and new newsletters and subscribers, which I also invite you to check if you can. And I finish with one brief slide on the next steps. So we are now moving to a new project phase. We are going from design and development towards manufacturing, testing, and demonstration. As I mentioned, we are about to install the new manufacturing line at Onyx facilities, and we expect that it will be operational by the end of the year. And in 2021, we will face testing activities based on current standards and new testing methodologies, as I explained in our package 5, and demonstration activities, which will finally be slightly delayed due to the COVID outbreak, but that should be operational in 2021 already. So that's all from my side. Thanks for your attention.
Okay, thank you very much, Maria.
I'm glad that you listened, because I was worried that nobody answered.
No. We have listened very carefully. That's very interesting, a very nice presentation.
Thank you.
We have a lot of material available at the website. We'll have to have a look, certainly.
Yeah, certainly.
Okay, so now we are moving to the second presentation of the second project. It's Be Smart. It will be presented by Laure Emmanuel Perret.
Good morning. No, good afternoon. Sorry.
Good afternoon.
So you can see my screen, yes?
Yeah.
Okay,
yes,
perfect. So thanks a lot for inviting me, and also thanks for this organization. It's not easy to organize an online meeting, but thanks to do it. And yes, I'm glad to share with you here some aspect of the Be Smart project. So what is interesting that these 3 projects, BIPV-Boost, Be Smart, as well as PV Adapt, are in fact kind of sister projects, because they reply to the same call of the Horizon 2020 European project. So our objectives are quite similar, are very similar. The way we tackle them is different. And here I will not be able to enter in the detail of the project. I just selected some aspects to share here with you. And of course, then I would be glad to discuss also more in detail some aspects. And so we try to take this project objective in a very holistic way, with different benefits we have identified for cities. So we want the Be Smart project to contribute to bring photovoltaics into the mainstream policymakers and stakeholders to reindustrialize a city in Europe. But it has also a lot of benefits for buildings, of course, bringing a BIPV into buildings, also significantly improve the ROE and through the generation of electricity. And just perhaps you will see that in my presentation, we are talking about EPOG, EPOG for energy positive glazing instead of BIPV, and I will explain you a bit why we use this terminology here. And the third benefits we identified and we are working for is, of course, the citizens, how we can also increase the awareness of citizens in their conscious choice of constructive materials to promote more sustainable living and cities. So this is our vision, and also for what we are working for in this project. So here the basics of the project is to go from traditional photovoltaics to a building material, a building element which is producing energy. And this is what is important here to understand. It's also why we decided to use different terminology in our project, not to talk about BIPV, even if it's a word that we still use, but more to talk about energy positive glazing, because module which is made to be installed on a facade or on a roof as first property of a building material, of a constructive element, and in addition of that is producing electricity. And for us, this was something very important, that the reference of this active element that we install on the facade of a building is not a standard PV modules which is produced to be implemented in a traditional solar plant, but more compared to a building construction material which is not producing energy, like for example aluminium alucobond facade element. So we try to demonstrate that we can make active building elements and that they are really interesting, of course, because they are creating value, and it is all the benefits of this technology. This is a summary a bit of some aspect of the technical activities that we are tackling in between the different work package of the project. So if we consider the before Bismarck, where we talk about BIPV and conventional BIPV, what we want to reach is to optimize and to bring a change in the technology, not by developing new technology, but more by transforming existing technology. And we started with all our development are based on crystalline technology. We choose this technology because it's a very mature technology today, the cheapest one, and the one that will probably stay on the market for the next 10 years. And so we wanted to take all the advantages of this mature technology today to see how we can transform it, to bring it to an active element for the construction. And of course, all this optimization process, and I will show you some of example, need to be evaluated and to be implemented while optimizing cost, because of course the main topic here is about cost reduction, cost efficiency, but also aesthetic, multifunctionality, and reliability, which are 4 parameters which are very closely interlinked. So we try to go from BIPV to active constructive material. To be able to transform this crystalline module into building elements, we are working on different aspects. Very important one is the aesthetic, which is brought through the color, the size, and the shape of a module. So the color is a high topic in our project, where we are investigating different way of making color into a module, using ceramic glass printing, digital printing, using different type of colored encapsulant or interferential filters. And so we have compared these techniques, developing some of these techniques or improving them. And in addition of the color, another element which is very important, as I said before, is the functionality of this building element, which has a functionality of construction. It is a roof. It replaces traditional tiles, or it is the skin of a building. And this element should not only have the functionality of producing energy or aesthetic, but could be also have properties like thermal insulation or acoustic properties. And so we try to combine this multifunctionality in one element. Of course, when we modify the color of modules, we tackle the efficiency of the module. So all the work which are done here is to find the good balance, the best compromise between the module efficiency, its aesthetic, and of course its cost. And for that, we are evaluating different color technology, but also different solar cells technologies, in addition of evaluating as well different way of interconnecting the solar cells, like using, for example, shingling or smart wire or multi-bus bar technology. And of course, we do a lot of work on the reliability and the manufacturing process. The longer lifetime, the better will be, and the lower the cost of energy will be. So we are making extended tests on different material at different level, at the material level, on the polymer, on the cell, on the modules, but also at the mini module and full-size prototype module level. And to optimize also the manufacturing process, we develop some simulation tools that can help to predict you also some temperature profile for the lamination process. And I will show you also an example of a new formulation that has been developed, allowing a lower temperature process and therefore reducing cost also of the production of the EPOG. Here in the table, you can see different techniques of different technology of bringing color onto modules, like colored encapsulants, filters, laminating interlayer in between the two sheets of glass, using printing, digital or ceramic printing. And so these techniques, which are techniques developed by the partner of the project, have been compared in terms of their cost, in terms of their aesthetic, lifetime, and power. And we have identified the most promising technology here, on which we are focusing now on the further development. And the technology here that we selected are the colored encapsulant that is developed by CSEM and as well by the company Solaccess, partner of the project, and also the ceramic printing that the glass manufacturer Saint-Gobain is implementing in their production line today. You can see here some images and of the first prototype, which have been made using this colored encapsulant developed by CSEM and also implemented by Solaccess, the company Solaccess. You see here that different color can be reached, more terracotta colors for roof application, and white, gray, or light color that can be also implemented in a facade of a building. Also, the big challenge of bringing this encapsulant into the module is to ensure their long life and their reliability, especially within UV and temperature exposition. But the first results that we obtain are very encouraging in this way. We see that accelerating aging with UV light and temperature also bring very good results. So already the company Solaccess is implementing in their production line some of the developments that have been done in this project today. I told also about how we can decrease these costs at the manufacturing level. And here our focus is on the formulation of polymer that can be processed at a lower temperature. When I say lower temperature, is between 85 and 120 degrees, which is quite different from the usual 160 degrees of other polymers that are processed in the PV industry. Being able to lower this temperature has, of course, an impact on the cost of the lamination process, and especially the energy used also for this process. And so here we are, you can see the image of the first extrusion of this encapsulant, which is a polyolefin-based encapsulant. And the first accelerating aging test also show that we have in a mini module configuration, we have no loss after more than almost 9,000 hours in the PID, which is something which is very promising and that we are continuing to work on. Another important step was to be able to make this modeling tool helping to optimize the lamination process of epoch elements. It is important because for a facade, or especially for a facade, the configuration of a module can vary a lot in the thickness of the glass or size of the glass. And the consequence of this variation is that for the manufacturer, it has to re-optimize his lamination process each time. And it is crucial that this lamination process is very well managed, because we know that difference in temperature or inhomogeneity could lead also to degradation within time. So this tool that we developed allow us to input some data like the glass thickness, the size of the glass, the family of encapsulant, the pressure also of the laminator, pressure, the profile that we will have in the pressure, and then it gives you a simulation of this lamination process, telling you at what time you would need to have your module on plate or to press. And the simulation and the experimental data has been shown to be very similar. So this is a tool which allow you to speed the optimization process at the beginning of a manufacturing session. Beside the technical activities, we are working also a lot on the exploitation. How can we make sure that the development in this project will take the place also within the industrial partner and on the market? And so we are also working on different business model that will be possible for the different stakeholders in the field also to bring also this cost reduction. And yes, we try to define what are the best strategy to make also market analysis and to consider all the risk and opportunities also for this exploitation plan. And I would like just to conclude with some examples. So these are not the demonstrator directly linked to the project. We are also working on 3 demonstration projects, which will be 3 new buildings with solar facade, one in Uppsala, one in Oslo, and one in Neuchâtel in Switzerland. They are just starting to be built, so it's a bit too soon now to show you images, but I want to show you other examples where the technologies that we have developed in the project has been also implemented, and where we have already the chance to make some pilot projects. So here, the first one is in Vineyard in Auvergne. It's a village where we have this village has a very high heritage protection, so you are not able to install the standard PV module on roof. And here the roof on the building on the right, on the left here, has a roof made with solar panels using this terracotta color. And so these colors of modules has also their application in the urban area where we have some limitation due to heritage conservation. And this is an example of the white solar modules developed here, commercialized by Solaccess. And it is an example of a facade. Here, it's not an integrated facade, it's applied on facade, but this was the first implementation also of this technology, which is now also on the market. And to conclude, I also want to mention that in this project, the communication aspect is very important, because we know that, I mean, it's clear that the technology is ready. We know how to use it. We have to understand a bit how we can improve it, perhaps not the technology, but more the process, to be able to conceive the active facade and buildings in a more smart way, faster, also in a faster way that will also contribute to reduce cost. So all the technology is ready, but still it's very difficult to be implemented. And we are convinced that communication is very important, education is very important, and also to be able to communicate about this technology in a more emotional way, like the work done here by Compass, where you see these this artwork made of 3 solar panels, integrated high resolution image. This is done thanks to the Kaleo technology developed by CSEM, and it has been exhibited in China, and it is also exhibited now here in Geneva. But it is a way also to show to any citizens, to architects, that this technology can be beautiful, can be integrated easily in our cities, buildings, can be even artwork in a urban area, and that at the end, probably the blocking point is, of course, not the technology, but perhaps just our creativity. And then I just finish by presenting you all the partners of the BSmart project. And we have also a website and social media where you are very welcome to visit and to follow. Thanks a lot for your attention.
Okay, Laura, thank you very much for your presentation, and it's really impressive way of meeting art and technology. It's really very, very nice final image. Okay, so I'm sorry we're a bit late in the schedule. Let's move to the next project, is PV-Adapt, that will be presented by Anthony Peppers from National Technical University of Athens.
Hello, can you see my screen?
Yes.
But I cannot see mine. Please hold. Okay. Thank you very much for giving us the opportunity to present our research project PV-Adapt. Let me introduce myself. My name is Antonis Pepas. I'm senior researcher at National Technical University of Athens. My expertise is energy and carbon analysis. Project coordinator is Merck Consulting House from Belgium, but as a member of technical coordinating team, I'll present our project. Now, as CO2 emissions, as CO2 emissions from building have risen again in the last years, it's imperative to find alternative solutions to achieve carbon neutral technologies by 2050. The investments of NZ buildings are growing. It's foreseen about for 2024 about 6 billion on the market about NZ technologies, but the BIPV technologies are failed till now to become a mass product, easily adapted by developers and architects. On this direction, PV Adapt and following set plan targets, which also the requirement of the call that PV Adapt was granted to fund it. We are focused on 4 main pillars. The first one is to integrate a heat mat with PV module able to produce both electrical energy and thermal energy. We are focused on prefabrication and modularity in order to customize flexible system based on the end user needs and to deliver construction products adapting also energy producing technologies. We are focusing on smartness because the combination between the electrical production and the heat production is something not easy to do it. So we need an intelligent system in order to manage the operation of the modules. And also we want circularity because we want to decrease the CO2 carbon footprint, to promote environmental financial viable technology by closing loops and giving new value to waste. On this direction, which is the concept of PV Adapt. We are trying to combine PVs, heat mats, and construction materials. On this direction, starting from the front of the panel to the back, we have conventional PV modules, which combined with aluminum heat mat able to harvest the thermal energy from the PVs. We have a wide area of passive components, mainly produced from waste material components. We have a steel frame that we put all these things together, and we have a joining process conducted on site. On this direction, we are trying to, let's say, make available to the market a Lego system which based on the necessities of each site and each case study, we can deliver prefabricated and ready to be installed and joined construction materials able to produce also energy, both electrical and thermal. What PV Adapt is trying to achieve? As I told you before, the first step is to develop building elements producing both thermal and electrical energy. We try to deliver new green construction components able to be assembled together with our BIPVTs. We try to create an aggregator software tool able to host a wide range of use cases and many control strategies based on the requirements of each case study for balancing thermal and electrical networks. We're trying to build viable business models and to exploit our results. And in order to do all that, we are developing self-learning forecasting algorithms that can predict both the consumption of the buildings with a minimum value of data and also the efficiency and the operation of our modules. And also based on the consumption, the balance between the consumption and the production of our elements, we are trying to establish and to deploy algorithms that can better match the energy supply and demand and to further boost the renewables penetration on self-consumption of the buildings. We're trying also, because it's a market product, to develop user interface able to support alternative business cases, easily to be handled both from the end users and the administrations that operate the system. And of course, because the BIPV should follow a wide range of EU standards, we are trying to conform it to existing standards and informing the creation of new ones when there is a lack. I will not stay here a lot. Our objectives, as I told you, are distributed in 4 main pillars. It's the production of the energy active heat mat and PV modules. We have the first results. Our prototypes are almost ready. You will see later some illustrations. We try to create a modular approach in order to assemble the PVs and the heat mats and the construction materials that we produce, like fiber reinforced geopolymers, fully developed by waste-based oriented strand boards, and loose fill material expanded per light, which can be used as insulation material between the BIPVTs and the back system of the envelope. As I told you before, we're trying now to develop the smart system that controls the whole idea, to deliver let's say an intelligent integrated project delivery software that will pre-dimension, will prefabricate and deliver the PVs and all the modules ready to be installed in efficient and with minimum cost on the site. Of course, we are trying to follow and to be aligned with the EU regulations and to fill the gap where there is a gap, especially on the efficiency. On when we will discuss on this later. Sorry, and to demonstrate our technologies on the real sites, but also in a living lab, as we will see later. Our roadmap for the project implementation, we're about in the middle of the duration of the project. We have some delays through the COVID, because of the COVID, so we have an extension. During the first year, we identified the BIPV requirements, we identified the business case scenarios and the whole evaluation procedure of our system, and we initiate a procedure for testing each sub-element before assembling the PVTs. During the first year, we were focused on the performance analysis. We built the whole methodology for performance reference versus the scenarios that we're going to implement in the test sites. We are collecting the first results, which will be used as a baseline in order to evaluate the efficiency of our products, for technologies in the living labs. We are trying to analyze the results from the living labs test in order to efficiently integrate the new panels in the demonstration sites. We're between year and year 3. We are trying to optimize the whole process. We're now producing the prototypes. We're putting into validation the prototypes also, and we're following audit process in order to evaluate their efficiency. And based on this data, we're trying to validate the energy and carbon footprint and also the end user response to our technology. By running all these tests in the living labs and the demonstration sites, we will evaluate the whole technology. We will try to reach a higher TRL and be close to the market, and to deliver innovative technologies which will boost the market, the BIPV market to the European Union. Our Holy Bible, the EU standards in relation to BIPV requirements. There are 2 main standards that we follow. It's EN 50583 part 1 and 2, which describes what means BIPV. But because BIPV is also a construction product, we will fully analyze and follow CPR 305, which will evaluate our modules as construction materials, and also IEC 63092, which specify BIPV's architectural applications and facades. By compiling all these standards, we analyze our demo sites. We analyze the functionalities that will provide to each demo site. We followed an architectural approach For example, you can see here one of our demonstration sites in Bilbao, where, first of all, we analyzed the architectural approach. We analyzed the installation, the adoption of the PVs on the roof and on the facade. We fully designed, simulated, and evaluated the PIDs and how the whole system will be integrated in the building operation and how we'll harvest both solar and electrical energy. This was done for all demo sites. I have to mention here that we have demo sites in Spain, in Portugal, in Greece and Austria, where will be installed more than 700 kilowatt peak capacity of our modules. Some initial results. You can see in the left top, the new Acorin system designed and tested by Coolhaven in Portugal. At the left is the first design of the heat mats, which will be adhesed integrated with the PV modules. We redesigned the junction box and the whole PV, let's say, structure in order to be able to adhere on behind it the heat mat. And also we have another one innovation product here. You have to see the video in order to understand. Later on, you can visit the demo site to see it. It's a green wall prototype, which is a fully automated system with solar panels in the front and plants on the back, which provide a new product and green facades on the buildings. Here you can see the first test of the big modules that produced. We have reached now in one system 4 commercial PV panels. We have proceeded also to the design of the assembly of the panels between them in order to ensure the water tightness and to provide the functionalities needed to the buildings. And at the right bottom, you can see also the geopolymers and OBS wooden, let's say, materials that's fully produced by waste and will be used as the back envelope of the product of the modules. All the system will combine together with the steel frame in order to provide a new construction solution for the buildings. Now, in relation to the management, we have built the use cases, which combines a lot of data. It uses the data from the forecast, weather forecast, in order to calculate the energy production, the energy price delivered for the modules, and also to interact with the aggregator in order to analyze the optimum result for cost reduction. We are building the boundary conditions of the system in order to see which is the limits of the kilowatt, both electrical and thermal, that can be delivered of our products. We built RC models that analyze all this data and provide information how the system will react based on each use case. And there is a secondary, let's say, level which also interacts with the building and provides information about the comfort level inside the rooms and how the thermal energy and the electrical energy of the renewables can be fully exploitable at the maximum percentage in order to obtain the comfort level we need at the building at minimum cost. We have already run the first test in Energeticum Living Lab. The system performed very well, let's say, promising results. Of course, we have a lot of work to do. We will run a wide range of experimental design in the Energeticum and afterward the demo sites in order to fully evaluate our technology. Now, this is, let's say, the concept of the whole system that controls the modules. As I told you, there is a decision support system that analyzes the weather forecasting, the consumption of the buildings, the market aggregation in relation to the availability of energy, the heat, the peak demand, etc. The user needs, like a single house, where we have the schedule how the occupants will want to operate the PV modules when they need thermal, hot water or electrical energy. We are developing prediction models for both production and consumption, and for each use case, we are optimizing the whole operation. We are operating the scheduling of the electrovalves on activation, and also we have an intelligent algorithm that also can be used for predictive maintenance of the PVs by evaluating the performance in specific conditions. All the systems are cloud-based solutions. However, I will not stay here a lot. We are building a controller that will be integrated in the demonstration sites in order to have isolated, let's say, an independent operation in case of lack of communication between the controllers and the cloud system. So it's a holistic solution that can be operated independently at building level. However, for further exploitation in the market and by having a massive number of buildings that we can handle, targeting to, let's say, heat delivery grid for hot water, we are building the cloud system in order to interact and analyze all this data in a more massive format. As our PV modules are both, let's say, energy producing technology, but also construction materials, we have a wide range of testing procedure. We will evaluate in relation to the efficiency of our PV modules in test rigs, in testing labs, in living labs. We'll evaluate also the performance of the modules in relation to the adhesion, because we have an adhesion layer between the heat mat and the PV module. We will have extensive testing in relation to weather condition, in freezing, etc. These tests are already implemented in our partners who have the facility to do it. And all these results will be analyzed in relation to sustainability index, in relation to three main pillars of KPIs: environmental, social, economic, by applying life cycle analysis. By concluding and not losing more time, I have to say that the main question is the cost. We know that the cost of the BIPVs is quite higher than conventional PVs. The solar thermal are more competitive. The construction material, the prices are quite lower than the BIPVs. So we're trying now to build a new technology that will keep the same price available in the market, but also will delivering both solar thermal energy, and also electrical, and to reach the set plan. I conclude because I spent my time. We're 18 partners within the European Union, from industrial partners, research institutions, certification bodies. Here are the contact points. Please feel free to visit and to take the information needed from our project. Thank you.
Okay, thank you very much, Antonis. I'm sorry we are too delayed in the schedule, so I don't think we have time for. There was scheduled some time for questions, but I think we will have to move this to the end of the session. So we have to go to the second part of the thematic session, which was a session related to the close-to-market BIPV solutions demonstrated on pilot buildings in Europe. I will ask the presenters, please try to keep to the scheduled time, so not to increase the delay we're having. So next one is PV sites by Eduardo Romano. Eduardo, when you like, you can begin the presentation.
Thank you, Alejandro. Do you see my screen now, or?
Yes. Yeah.
Okay. So, I'm going to explain PV sites project. PV sites project is a project already finished 3 months ago. So in this sense, it's different from the previous ones. And I can say now that I see several common aspects with the rest of projects, but in some way, the focus of this project is different from the others. I will try to explain. Well, this is the outline of my presentation. First of all, a very light introduction. Then I will go through the objectives and challenges of this PV-size project, and explaining also the main outputs and achievements so far, highlighting also products that are already in the market after the end of the project, which is the main, let's say, objective, target of the Commission when they fund this kind of projects. Well, this is the first slide showing several figures, mainly the funding obtained from the Commission and Switzerland, in total around 7 million euros, and the consortium. The consortium at the end is, as all the projects, tries to cover as much as possible the value chain, the whole value chain, from manufacturers to RTOs, partners dealing with exploitation, with and so on. So this is also our case. In our case, we have two module manufacturers, Onyx and Frison. As you can also see, these partners are also in other projects. So that means that they are very good partners in that sense. And well, we try to cover also the whole. We try to select partners from whole Europe. So in our project, the main target was to drive the BIPV technology with the high potential that we know that it has to a large market deployment. And well, this is something that the time that when the project was presented, was submitted, was 2015. I think the focus was quite a bit different from it is now. The focus was more in developing solutions, demonstrating that there were solutions, accomplishing with the BIPV concept, more than maybe focusing on cost reductions or other aspects. So this was the main target of the project, to demonstrate a portfolio of BIPV solutions covering the whole range of the BIPV. So, I mean, modules, power conversion devices, so inverters, energy management system, software tools for simulation and for energy calculation, and even the LCA was already included in this analysis. And initially, we identified different market challenges. For instance, the need of flexibility in the design of solutions and systems, without forgetting the aesthetical value, the multifunctionality of these solutions, and the cost effectiveness. Very important to put a product in the market. Also, the need or the lack of good tools for the design of BIPV systems, and also for the energy calculation and energy performance in buildings calculation, able to assist the designers, architects in the very first initial stages. Once we have produced the electricity from BIPV, the question is what to do with that electricity. So, and for that, we also work on more predictable, manageable, and grid-friendly, profitable BIPV generation systems, especially energy management systems and different tools for the planification of BIPV systems with the storage. And finally, all these solutions had to be demonstrated in real buildings as much as possible. That we'll try to. So this is an example of the different solutions we achieved in the module topic, let's say, or product. So these are different glass crystalline silicon solutions developed by Onyx. We can see here hidden bus bars and interconnections, or back contact solar cells in see-through glass solutions, or PV modules with large formats. This is something that is demanded by the market, by architects, especially for glass envelopes buildings, and also modules with glazing treatments. All these solutions were developed, has been developed during the project. These are more pictures and examples of what Onyx, together with other partners, have developed in the project. This is a semi-transparent, low concentration system, passive solar system developed by Technalia and Onyx. In this case, the TRL of this development is still in 5, so we only tested in control conditions, in test benches, control conditions, but not in real buildings, let's say. This is the family of products developed by another manufacturer in the project. In this case, it's Flisson, the Swiss manufacturer. They are CIES on metal BIPV modules. Here we have several examples, for instance, roofing shingles on CIES on steel, or different models of roof tiles on different metal sheets, and finally large area flexible membranes, especially for industrial and canopies, industrial buildings. But these are examples of the modules testing in test benches, in Acciona, in Technalia, and ICEA, different laboratories, outdoor testing laboratories. Up to here, we have seen the developments in module level, but as I mentioned before, we also have developed different solutions for the balance of system. In this case, we have developed two kinds of inverters dealing with or playing with the storage. One in DC coupling, developed by Technalia, and the other one in AC. So the storage is coupled in AC, developed by SEA, Ines. Both systems show high reliability and efficiency, trying to get and achieve a cost reduction at the end of the industrialization process. In the building energy management system topic, Technalia, together with Acciona, R2M, developed different solutions, tools, combining software, hardware, and firmware for the suitable management of the energy produced by the BIPV systems and the suitable integration of this electricity into the building energy system. These are different examples of what we have achieved so far in this category. For instance, a planner tool for BIPV systems with the storage in order to size suitably the amount of batteries needed in a given application with BIPV, or different forecasting tools to know and to combine the generation in advance with the consumption in a building, at least with 24 hours in advance. This is our forecasting proposal. This is, for instance, maybe you know this software is a BIM-based software tool. It's called BIM Solar. It has been developed by Commission and Energy companies. And it's very useful, especially in the very first stages of the design, to analyze and to see aesthetically and also from the energy point of view if a solution, if a given solution is profitable or not in a given building. Here you can see several examples showing what I have mentioned. And finally, all these developments, modules, inverters, energy management systems, the software application for designing has been tested in real buildings. The buildings we have used, I think we have tried to cover the whole range. So from residential, single family and multifamily buildings, also industrial buildings. We have one, canopies or another kind of buildings. And finally, from the tertiary, we have an office buildings, the headquarters of Technalia. In most of the cases, they are retrofitting works. And I will show just examples of the final pictures. So this is the single-family residential building in Belgium, in Stambrugge. So here the solution is CIES roof tile combined with batteries and the inverter we have developed, Technalia in this case. Here, so you can see the nice result we have achieved with this solution, CIES solution. It's especially important to highlight the good integration. At the end, it seems that there is no PV panel on top of the roof, but at the end is the CIES solution which is placed. So this is another kind of buildings, more for the electrical vehicles, carports. we have a couple of them covered by these CIS solutions provided by Frison. These are two. In the website, you can see, as I mentioned, the project is already finished, but you can see many public information videos on the installation process from drones. I mean, you can see a lot of information from each demo site. This is the industrial building in Spain. It's the Cricursa headquarters. It's a glass manufacturer in Catalonia. And here we have placed a BIPV industrial roof, also with a Frison solution. Someone could say that maybe this is not exactly BIPV because in this case we are not replacing any component. We are just placing the membranes on top of the roof. But I have to say that it has been done very aesthetically, taking care of any aspects in the design of these tiles, let's say. So it's not just placing the tiles on top. There is a lot of work behind. Oh, this is the multi-family building in France, near Lille. It's a social housing building. It's an opaque facade and has been covered by a ventilated facade made by Onyx with glass crystalline silicon modules. This is the office buildings from Tecnalia. It's the headquarters in San Sebastian. Here we have covered a couple of facades with again with a ventilated facade. In this case, it's transparent ventilated facade with contact cells. Here you see the final aspect. So this is the initial aspect and the final aspect. But we also have, well, from the exploitation point of view, because at the end we have already finished. I can say that we have identified more than 25 exploitable results from companies, and we have developed within the project a clear roadmap for the commercialization of these results for each company with the market analysis, intellectual property right analysis, also marketing plans, financial plans, the freedom to operate of some of them. So I think we have worked a lot on that with a specialized partners. For instance, in this case, we had R2M in the consortium for making this good job. And also very important for us, we got the exploitation of and the commercialization of PV-sized products even before the project finished. So with 2 years before the project finished, we already had different products in the market. In this case, I am showing different BIPV panels from Frison and from Onyx. In the first picture, for instance, we have the headquarters of Lego in Denmark. They are covered by a crystalline silicon photovoltaic skylight using a black free module. Or, for instance, this blue tinted crystalline silicon installed in Balenciaga Stair Front in Miami. They won here a prize for this with this curtain wall. Or different installations from Frison. Here you see these flexible CIS modules on a flower market in Johannesburg, for instance. Additionally, we also got the commercialization of different products within PV sites. In this case, Tecnalia, for instance, signed a license agreement with a Spanish company for the use of this planner tool adapted to PV systems. Or the licensing of the BMS, the building management system, also from Tecnalia with other companies in Spain. The inverter we developed in the project is being nowadays industrialized by a Spanish company also in the Basque Country. BIM Solar platform, you remember this BIM platform is now ready and is online for free. There is also a version that has to be paid, but in this case, with the free version, you can do a lot of things. Please, if you want to try. And very important, and the Commission also gave a lot of value to this, is the agreement between R2M and Onyx Solar for the commercialization of Onyx Solar products in Italy and in France. This was a big milestone achieved during the project. Also, this has been mentioned by other projects. This project was achieved for one of the first times the testing of several products according to the new European standard on BIPV 5583. And additionally, we also work on innovative BIPV standards for all the products, and that could be nowadays applied to different solutions. In terms of publicity and in terms of communication and dissemination, we also, these are final figures, although they are still increasing. For instance, the PVSite's website had more than 50,000 views, and we had all the deliverables, public deliverables and public information. We have more than 72,000 downloads of this information, almost 50 publications, scientific, peer-reviewed, and generalist. And we also have produced videos, general videos about the project and also about the demo sites. Here you have the links, and you can see them in YouTube channels. We also, in the last period of the project, we prepare different webinars and on-site workshops using the demo sites and the visits. We also perform guided visits to the demo sites. And finally, we have, this is always the same, we have participated in almost 70 events along the project. So a great success in terms of dissemination and communication. This is, I think, one of the most important products and outputs of the project is called this PVSite's catalog. At the end, it gives useful information for the selection of optimum products at project design level. And it's like a book. It has, well, it's an online book and provides information on the different products. So there are data sheets that describes the different products, a description of each product and how is used within the demonstrations, and also an overview of the installation process of all the products. This is the general view of this ebook. Well, I think it's already in the web, so I don't have placed here exactly the link, but I will do it after this workshop. And finally, this is the last. I think the last slide is already in 2015. That was when the project was submitted. The life cycle analysis was already important. Nowadays, it's even more important than in the past. And the results we have obtained here is that, well, we have carried out the performance assessment in two levels, one at module level and another one at PV system level. So at module level, we can say that for the majority of the categories, the impact categories, the results on this LCA shows that the CIES technology has lower impacts than the crystalline silicon technology, according to the results achieved so far. And at system level, it has to be highlighted that the high influence of the surrounding factors for this analysis. So the radiation, the installation, the location, the climate conditions, all these parameters affect the LCA. So I would say that the LCA analysis is a case-by-case analysis. It's not just to say the BIPV is better than other PV systems or other kind of integrations. It's case-by-case and country-by-country, location-by-location. And I think that's all. So you can visit this website, pvsites.eu, for more information, and you can download there a lot of public information. Thank you very much.
Okay, thank you very much, Eduardo, for this very impressive presentation with a lot of very, very interesting results and demonstration. I'm sorry we are still very late in the schedule, so we have to move to the next project presentation. Is energy matching that will be presented by Laura Maturi from EURAC. So, Laura, yeah, we see already your presentation.
Laura,
I'm sorry.
Yeah.
Okay,
Can
okay.
you hear me? Okay, okay. So good afternoon. I'm Laura Maturi. I'm senior researcher at the Institute for Renewable Energy of URAC Research, based in Bolzano, north of Italy. So I'm coordinator of energy matching project that is an Horizon 2020 project. So I give an overview on the energy matching, but first I would like to give a short overview on URAC activities on BIPV and how we came to this project Horizon, this energy matching project. So this is an overview on the project we were working on within URAC in the past 10 years on BIPV topic. And so basically what we have seen in the past decade is that at the beginning of the decade, at least a lot of our research focus was on the technology development and so development of new product, new PV modules, new substructure solutions, new components, and so on. And also a lot of focus was on aesthetics, because it was clear, it had always been clear within the BIPV sector that the public acceptance of BIPV was a key factor to succeed in market penetration of this technology. Because of course, if people have a negative perception of this technology and they think that the PV is ugly, then they would like to see them placed in their buildings or in our cities. So a lot of research focus at the beginning of the decade was on architectural integration issues, so on aesthetics and technology. But in most recent years, another aspect of integration arose, that is the energy integration, meaning the ability of PV to be integrated not only into the envelope of the building, but also to be efficiently integrated in the overall energy system of the building. So meaning the ability of PV to interact with the building loads to maximize self-consumption and producing energy in the time when you actually need it. And on the other side, to efficiently use the energy that is produced on site within one or more buildings, so also within a district of buildings. So given this experience, we really believe in a multi-level integration concept of BIPV. So building integrated PV means for us that integrated should be a word indicating integration in these three aspects, so in the technology, aesthetics, and energy integration. So this is how we reached, this energy matching project. This is the first Horizon 2020 project where we started really to focus a lot on the energy integration concept of BIPV. So with this project, we really started to look at somehow try to maximize the matching between the PV production within the building with the building loads consumption. So somehow, if you look at the red curve of a building consumption, for example, and the yellow curve on PV production, our aim is really to enlarge the green part, meaning to shape differently the curve to maximize really the matching between production and consumption. So we have a consortium of 17 partners within energy matching project that I would like to acknowledge. So we have a research and development institute at the university. So we have Tecnalia on board, the Larna University as main research and development institutes. Then we have building company, big building companies, that is Bouygues based in France, and we have several industrial partners that you can see, for example, Ferramp, Nibe, Tulips, Plastica, Eurofinestra, and Onyx as a PV producer, and Pellini, SolarWall. Then we have exploitation and dissemination partners, R2M Solutions, and WIP. And then we have three social housing buildings companies based like that are supporting like the demo implementation of our solutions. So very quickly, the project background. So as we know, European policy is boosting the reduction of European building stock energy demand. And we are aware that buildings have to become active elements of the energy network. So not only to consume energy, but also to produce energy. Also in a view of energy sharing and energy communities concept. We are also aware that the residential sector holds a huge potential to meet the European policy targets. And so that's why how energy matching project will contribute to overcome these issues by developing and demonstrating methodologies and active envelope solution to maximize the renewable energy sources harvesting in the built environment, optimizing the energy matching, so between the energy production and the building loads as I mentioned before. And the target of the project are the energy retrofit of residential building sector. So the three main objectives of the projects are, first of all, development of adaptive and adaptable envelope solution for energy harvesting at building level. And second main objective is integration of this developed harvesting solution into the building and district energy concept. And then, of course, to enhance replication potential of the developed solutions. So these slides show in a very syntactic way all what is the project about. So in order to reach the three objectives that I have just mentioned, we identified 7 main results that we are developing within the project, and that will also help us to achieve the 7 main impacts that we have identified. So the impacts are basically related to several aspects, so energy aspects, improve energy performance, but also comfort and indoor environmental quality aspects, economics aspect, market, and society. So in the next part of the presentation, I will give an overview and on the current status of the 7 results that we are developing to really achieve the 3 main objectives that I mentioned before. So the 7 results can be divided into 3 main categories. So the first category is on grouping results 1 and 2. About methodological framework and business vision of the project. Then the results from 3 to 5 about the development of adaptable and adaptive skin technologies. And the third like results category about the development of building and district energy LAN. So let's start with the first 2 results on the methodological framework and business vision. So the first result is the so-called energy matching platform, and the second one is the so-called energy matching tool that I will present now. So I will start with the energy matching tool. So this is a tool that we have developed within the project to optimize renewable energy harvesting at building and district scale. So through an optimization process, through this optimization algorithm that was developed, we can support BIPV early stage design, especially to identify the best PV capacity and position, and the best battery capacity given several techno-economical input, and always in a ratio to maximize the energy matching. So trying somehow to work on the production curves and the consumption buildings curves to let's say maximize the green part that you see in this graph. So this is done in a also like cost effectiveness rationale. So an important milestone that we reached during this year is about the development of the energy matching platform that we have now an alpha version of this platform developed. So the platform is currently under like testing phase. So if someone is interested in taking part in testing of this platform, you are very welcome to let us know that you can be included in this process. So basically, through the platform, you are able to visualize a lot of results of the project, and especially also to access the energy matching tool that I've just shown you before to perform simulation on your buildings. So now going through the next results, this is a versatile click and go substructure, so that the partners Tulips, together with the other partners of the project, is developing this click and go substructure to host active elements, so PV modules that are developed within the project, but also non-active elements in order to enhance the aesthetics of the overall solution, both for facade and roof system, to reduce installation time and to be able to adapt to different envelope typologies. So we are currently in the phase of implementing this solution in the 3 demos that I will show later. Another result related to the scheme development is the solar window block solution. This is a multifunctional prefabricated insulated system that integrates PV modules, and dynamic and automated shading systems, and decentralized ventilation units, with the aim to maximize indoor comfort and building energy performance without adding electrical loads to the building. So this is conceived as an autonomous system from the energy point of view. So this is developed within several partners of the project. So Eurofinestra in particular, Onyx, Tulips, and Urac. So this is and Pellini. This is this slide summarizes the development process. So we started really from sketches through development of design, through several simulation on performance and modeling optimization. Then we had first definition of a catalog of solutions, integrating PV in several ways, such as the one that are shown here, so in vertical, on the overhang, and so on. After that, we have had the realization of 3 mock-ups that are realized and tested at the URAC Outdoor PV Integration Lab. And now we are in the implementation phase of this solution in the demos. This is in particular is the implementation in the Italian demo. So here you can see the 3 prototypes that we are monitoring at URAC, and the preliminary testing results that are quite encouraging in terms of energy performance of this solution. And this is a prototype presented at the Klimahaus Fair this year in Bolzano. So jumping now to the next results, this is the BIPV click and go system. This is about development of BIPV modules integrated with the click and go substructure. So here we are developing two types of PV modules, one by Tecnalia, the composite PV modules to be integrated with the tulip substructure, and the other one by Onyx that are glass lightweight BIPV modules to be integrated with the tulip substructure. The aim here is to reach a high aesthetical value, to have a flexible solution in terms of material, shape, size, and color, and of course multifunctionalities. Also for this case, there was a lot of work done this year by Tecnalia, Onyx, and Tulips on testing activities and so on. And we are approaching the implementation of this technology in our demo site. So I don't have still a lot of pictures to show about that because it's not yet implemented, but we will have really nice pictures next year when we will finish the implementation phase in the demo sites. Going now through the other two results related to the building and district energy LAN. So the first one is a renewable harvesting package to heat and ventilate. So here is about coupling of a solar thermal facade solution with the energy building system, in particular by coupling this solar thermal collector with the heat pump to by using the preheated air by the so-called solar wall thermal solution. And the second result is about building and district energy harvesting management system by the company, Swedish company Ferramp, to optimally manage the produced energy within one or more buildings. So also considering like a district with more buildings. So this year we reached another milestone about this solution. So that is about software and hardware of building and district energy system ready to be tested. So you can see there is the system is based on a DC grid with the optimized control strategies to match so the production and consumption within one building or more buildings. So with the final aim to maximize self-consumption, so maximize the on-site use of the produced energy and minimize the energy fed into the grid. So this was an overview on all 7 main results that we will demonstrate we are demonstrating in 3 main demos that are located in 3 parts of Europe, so Sweden, France, and Italy. And so we used the result 1 and 2, so the methodological framework basically to support the design of the 3 demo site buildings. And the other 5 results are demonstrated in the several parts of the 3 buildings. So this is an example how the energy matching tool, for example, was used to support the demo design implementation. So for all 3 demos, basically we started by performing simulation with this tool to guide us on understand where and how much PV to integrate in the buildings, with the aim to maximize the energy matching, so the matching between production and consumption, and yes, so this was quite a valuable tool that we developed really to support the technology's implementation in the 3 demos. So these are the 3 demo cases. So the first one is located in France, in north of France. Is all the 3 are residential buildings. So in this case, we have 2 buildings in France, 1 building in Italy, located in Florence, and in the Swedish case, we have 3 buildings that are not visible in the picture. But anyway, in this case, it's an interesting case because we have 3 different buildings, and we are connecting the 3 buildings with a DC grid, and we will demonstrate the FERRAMP concept of energy sharing between buildings. So in July this year, we started with the energy matching solution implementation in the 3 demos. So we can start seeing first transformation of buildings. In particular, this is the Italian demo site, where you can start see the transformation. First, now we have applied part of the solar window block, and we will now continue with the implementation of the rest of technologies on solar wall, PV, BIPV click and go solutions, and so on. And we also had delays, of course, due to COVID in implementation, but we plan to finalize all implementation by next year. So that's all from my side. I thank you very much for the attention, and you can find further information on the project on the project website. And I would like to acknowledge once again the project partners of energy matching. So thank you very much for your attention.
Okay, Laura. Thank you very much, Laura. I think we are very out of the planning, but somehow I think there's a short time for a short question for Laura, I think, Regis.
Yes, exactly, Laura. Yeah, there is a question for your project. So how is the comfort and indoor environmental quality enhanced in the energy matching project? That is the question we got for you.
Yeah, so I can make an example, probably with the results that we are now in the phase to implement. That is the solar window block. In this case, we are also looking at daylighting conditions, so to improve indoor daylighting condition, indoor, of course, thermal comfort. And this is basically related to all technologies that we are development. So these are the main as this is an example, and yeah.
Thank you very much.
Yeah.
I will give you back control, Alejandro, for your presentation of Tech4Win.
Okay, thank you very much, Regis.
Thank you.
So, now you can see my presentation?
Yes.
Yeah.
Okay, so I will try to be a bit more brief to compensate a bit the delay we have. So now we are moving to the last part of the session. Is the topic is a bit different. I would say it's a more in a more fundamental technological level. We need, in this case, we are dealing with applications of smart solar windows, where we want to integrate the PV functionality in the window, inside the window. And this means that we need really to go to new technologies. So the first of the projects is Tech4Win. It stands for Disruptive Sustainable Technologies for Next Generation PV Windows. And here, well, I see the outline of my presentation. I will briefly present the introduction of the topic, and I will go soon to the which is a very strong short summary of which is the strategy we are proposing in Tech4Win, the concept of the project and the underlying technological principles. the objectives in the KPIs and quantitative targets that we have defined in the project. I will also comment about the Tech for Wind Consortium and which are the main roles. And I will have special emphasis, which are the main results at this moment of the project. So now here we are dealing with transparent PV. Transparent PV is a new paradigm in PV deployment for the opening of solar markets that is required to consolidate photovoltaics as a real alternative to non-renewable energy technologies. And as you can see in the graph that is shown in the transparency, there are several fields of application for transparent or semi-transparent products. And one of the ones that have a more interesting potential is that related to the development of smart solar windows, or what's called here the window integrated PV. And in this case, this implies the need for systems with a relatively high level of transparency in the visible region. We are between 50 to 80%. Mainly applications, I would say, would move between 60 and 70% of transparency. And we need technologies allowing achieving efficiencies higher than 6% would be somehow the threshold. But okay, of course, as high as possible. So why this is interesting? Essentially, this is related to the development of the new set energy buildings that require to increase the effective area in the building for collecting sunlight. So in this case, what we propose is to be able to replace all the windows in the facade by solar windows. And this requires that we need technologies allowing us to have a very high stability, because of course we need to go to lifetimes compatible with the lifetime of a window, which is as minimum 25 years. Very important is the non-intrusiveness of the products we are proposing. So we want to have any kind of visual impact of the PV functionality in the window. Then we need, of course, a high level of transparency, higher than 50%, and we have to go to as much higher efficiencies as possible. So at this moment, there are semi-transparent technologies, and in the previous presentations, I think I've seen some examples, in fact, of semi-transparent examples. And as you can see here in the graph, there is the problem is that there is a strong decrease in the efficiency when you increase the transparency. So when you go to transparency levels higher than 50%, the efficiency at this moment drops down 5%. Solutions that we have already in the market are mainly based on what we call non-selective segmented devices. In this case, the transparency is achieved combining transparent or opaque regions in the device. This is a solution that can be interesting for facades, but of course it's not viable for windows, for transparent windows, where you need to have the vision through the window has not to be hampered by the presence of the modules, of the opaque modules. In Tech for Wind, what we propose is a disruptive concept that is based in the integration of a tandem-like structure in the window that combines an ultraviolet selective solar cell with an infrared selective solar cell. And the targeted goals that we are defining at the end of the day is to demonstrate at cell level an efficiency higher than 10%, combined with a transparency higher than 60%. And as you can see here, the red star would be the results of Tech for Wind in front of the state of the art. What we are proposing is really to have a very strong increase in the efficiency that we're achieving at this very high transparency level. So about the strategy and the project concept, what we propose is the combination of an inorganic ultraviolet selective multifunctional coating that will be deposited on the first glass on the window, and an organic infrared selective solar cell that is implemented at the second glass of the window. The ultraviolet multifunctional coating has essentially two functions. It has to work as an ultraviolet filter, allowing any kind of ultraviolet radiation to reach the infrared selective solar cell, and also as an ultraviolet selective solar cell. And to increase the efficiency of the infrared bottom cell, we are also integrating optical management strategies, and basically this is done by the integration of a distributed back reflector at the back of the cell, trying to recover any kind of infrared photons that are not initially absorbed at the infrared cell. The motivation of the project essentially is to exploit the infrared efficiency potential of organic-based solutions with the well-demonstrated robustness and stability of inorganic thin film solutions that combine sustainable and industrial compatible technologies with demonstrated potential for cost reduction. The main innovation of the project relies in the capacity of this tandem-inspired structure to protect the most active PV layer, which is the infrared selective organic cell, through the filtering of ultraviolet radiation by the ultraviolet multifunctional coating. And what we want by this way is to extend the lifetime of the PV hybrid device from 10 years, that's the target defined at the end of the project, until 25 years, that could be the long-term target. We are using processes compatible with industrial deployment. Essentially, we are using two kinds of processes: sputtering-based processes for the deposition of the ultraviolet multifunctional coatings and of the multi-layer, multi-stacked layer structures integrated in the distributed Bragg internal reflector, and printing-based technologies or roll-to-roll solution-based processes for the development and manufacturing of the infrared selective bottom solar cells. Related to the objectives, the main objective of the project is to develop a set of transparent PV window prototypes with different size formats, up to a medium-size format of 30 × 30 square centimeters, with strong improvements in the level of transparency and visible quality in the visible region, energy generation, advanced filtering capacities, thermal behavior, and energy impact that will be tested in a relevant environment for demonstrating their feasibility as a smart window. For this, what we want is to develop critical raw materials free hybrid UV and infrared selective PV cell prototypes, which can be integrated within a wide portfolio of smart windows, allowing to meet the requirements and standards that are demanded by the construction sector. So here at the project, we have defined what we call the Tech4Win roadmap that covers, is a very ambitious roadmap that covers from the proof of concept to the mass market penetration. The roadmap is structured in 4 phases. Now we are in the first phase, which is the corresponding to the Tech4Win project phase, which has a duration of 3.5 years. Is the concept validation phase, where we are starting with a very low TRL. TRL starting was 3, and we want to achieve at the end of the project a TRL value of 5. Next steps would be the growth project phase, which is related to prototyping and upscaling, which would involve a improvement of increase of TRL up to a value of 7. The next will be the market uptake with improvement to TRL 9 with technology optimization, and that's after this the mass market penetration, which is forecasted in about 4 years' time. So we will focus in what's related to the Tech4Win project phase, even if we have identified not only the quantitative objectives that have to be reached at this phase, but also at every one of the other phases. The main quantitative objectives are summarized in this slide. At the end of the project, in terms of photoconversion efficiency, we want to demonstrate at cell level of photoconversion efficiency higher than 10%, combining an ultraviolet selective top coating with 2.5% of efficiency with a bottom infrared selective device with a 7.5% efficiency. We want also to reach very high transparency. We want to demonstrate in this term a medium-sized window prototype with a size of 30 × 30 square centimeters with an average visible transmission higher than 60%. This is the figure we are using. The average visible transmission is defined as the integration of the transmission spectrum waved by the photonic response of the human eye. In terms of lifetime, we want to demonstrate at prototype medium-sized window level a project lifetime of higher than 10 years at the end of the project phase, even if this will have to be extended up to 25 years in the long-term target. We need also to have a very high optical quality. We want to be sure that windows are really transparent in the visible and have any kind of coloring effect. So they have to be color neutral. This we are measuring by the color rendering index. We want to demonstrate in the prototypes a value of the CRR, the color rendering index, higher than 70, which corresponds to a high optical quality window, and so ensuring unhampered transmission of the visible light to the window. In terms of size, we are working at cell level, mini module level is 5 by 5 square centimeters, and these are essentially lab scale devices. And we are also doing a first upscaling to a medium size module level of 30 × 30 square centimeters for the window prototype, which is what we call the medium size format in the project. And in terms of manufacturing costs, we want to demonstrate processes and materials compatible with manufacturing costs between 250 and 300 euros per square meter at the project level, even if moving to competitive products, we will have to go to manufacturing costs below 200 euros per square meter, which is the long-term target that is defined in the project. So this is a relatively small consortium in contrast with all the other projects. It's only 8 partners, and you will recognize some of them have already appeared sometimes. We are IREC, we are the coordinators, and we are in charge of the development of ultraviolet multifunctional coatings. We are using for this essentially oxide-based strategies, and we are also in charge of the assessment of the upscaling of the sputtering processes. Onyx, that has also relevant participation in other projects, is acting here as industrial coordinator. They are the exploitation and innovation manager, and they are also in charge of the prototyping and demonstration activities. So they will be in charge of the implementation and assessment of the PV window prototypes. We have also participation of CEA in France. They have a strong background in OPV technologies, OPV solar cells, and they are mainly in charge of the development of the infrared selective OPV devices, and also in the optical modeling of the optimization of the device architectures. IMEC is also involved in the consortium for complementing the strong collaboration with IREC, in fact, in the development of the ultraviolet multifunctional coatings. In this case, is IREC, we are working essentially in oxide-based strategies. IMEC are working essentially in chalcogenide-based strategies, and they will be also in charge of the scaling of the sputtering processes. We have also the participation of Technica, Technology Center in the Basque Country in Spain, which are in charge of the development and implementation of the internal BRAC reflectors for boosting the efficiency of the infrared device. And we have 3 companies more. Armor is a big company with a strong experience in manufacturing of OPV-based models. They are in charge of the transfer of the OPV processes that will be developed at cell level in CEA to roll-to-roll industrial process conditions. So they have to ensure the compatibility of the process to the industrial deployment. And they will also be in charge of the scaling of the processes for the development of the medium-sized models. We have also Advent, is a chemist company, organic chemistry company that is in charge of the design and synthesis of the new high conjugated polymers for the optimization of infrared selective devices. And finally, Kenosystec is an equipment company, is in charge of the industrial techno-economic assessment of the sputtering processes, and they will also in charge of the design of the industrial equipment that will be required for the industrial implementation of the processes that will be developed in the project. So at this moment, we are more or less on the half of the project. I will present which are the main results that we have achieved in terms of the development of the infrared and ultraviolet cells. Relating to the infrared cell development, the main objective at cell level is the development of the infrared bottom solar cell with the infrared internal BRAC reflector that have to be integrated afterwards into the window solution. And quantitatively, we want to demonstrate a critical raw materials free proof of concept device at lab scale with an efficiency higher than 7.5% and with a visible transparency higher than 60%. And also what's very challenging, we need to work with processes and architectures compatible with lifetimes, compatible with the long-term targets defined of 25 years. So at this moment, we have had a very strong activity in the identification of the donor polymers for the active layer. So we want to have polymers, we need to have a very high transparency level. So polymers have to have absorption essentially in the infrared region. So you can hear in the transparency, the normalized absorbance versus wavelength of the most optimal polymers that have been identified in the project. In the black, you can see which is the eye sensitivity, which is essentially centered in the green spectral region of the visible region. We have identified 3 interesting candidates, which one was what we labeled is X39, which was developed in the project. There's also commercial polymer on the PTV7PH project from products from Mozilla. All of them have very low absorption in the visible region, which allow to be compatible with the transparency target that we defined in the project of 60%. We have evaluated the optoelectronic properties all these polymers and the potential for making OPV devices. So we integrated them in first non-transparent device test structure devices, which are represented. This is a schematic representation in the transparency. This, in fact, this is the first. Still is not transparent because we are putting a top electrode, which is a silver electrode in the top. So in all cases, we have been playing with an optimization of the architecture, optimizing the whole transport layer and the electron transport layer. Also, there has been a strong activity in the optimization of the composition of the active layer, which means identifying the observed the donor, the acceptor that is combined with the donor polymer, and the ratio between the donor and the acceptor, and also the thickness. And at this moment, we have achieved very interesting results using the commercial polymer in combination with a PCBM acceptor that has allowed us to obtain the very promising values of transparency, which are as high as 71%. This corresponds to this value here in the plot, with an efficiency which is about 6% for the conversion efficiency. For the other material, the PTB7 material that was identified in combination with the ACO acceptors, we can obtain a much higher efficiency. This is very interesting. The value of efficiency is 8.24%, which is even higher than the target efficiency in the project, even if the transparency is lower. We are just below the 60%, it's 58% of transparency. Other interesting issue is related to the optical quality. Here you can see a photograph image of the absorber layers with the combination of the donor acceptor polymers deposited on the glass. In this case, corresponds to the commercial polymer with PCBM, and you can see that it's really a high quality layer with almost no color effect, so it's essentially color neutral. So now, at this moment, what we are working is analyzing the compatibility of these solutions to the industrial requirements, because what we need to go is towards a solution that is compatible with the roll-to-roll processes that will be developed at the industrial site. In relation to the multifunctional UV coatings, the objective is to develop coatings with two functionalities, working as UV filter and UV selective photovoltaic solar cell. The final efficiency target in this case is lower because, of course, the energy part of the ultraviolet spectrum is lower in the sun radiation. In this case is 2.5%, and we want to have a very high ultraviolet absorption, higher than 99%. To achieve this, we know that we have to work in our optimal band gap region between 2.7 and 2.9 electron volts, and for this we are working into strategies. One is developing xenoxosulfide solid solutions, essentially it's related to the oxide-based strategy, and the other is with zinc sulfoselenide-based solutions, working with chalcogenide technologies. So at these moments, we have developed the first coatings with very high filter functionality. We have already demonstrated higher than 99% ultraviolet absorption, and we have also demonstrated the first ultraviolet selective solar cells as proof of concept of oxide-based ultraviolet solar cells. So this is the results obtained at solar cell level for the oxide-based strategy. This in the left-hand side, at the top left, you can see the device architecture that we have developed. We are working with an oxosulfide absorber layer. With these layers are synthesized by reactive sputtering, and we have demonstrated the possibility to control very well the sulfur to oxygen relative ratio. We can switch from ratios of 30% to sulfur up to 90%. So we cover a very wide range of band gap values and compositions. In this case, the layer we have in this device, it corresponds to a 60% sulfur partial content, and which leads to a 2.8 electron volts band gap. And this is integrated in a device that has been synthesized on FTO substrate, combining a nickel oxide whole transport layer and a B-layer a compound electron transport layer combining a C60 and a BCP layer. So here in the right-hand side, you can see a CM cross-section of the device structure, where we have colored with different colors, easy identification of the different layers. The xenosulfide layer is what's very interesting is that we can achieve really very compact layers and very continuous without the presence of holes. However, we already have seen that we need to increase the grain size because the grain size is really very small. And the main limitation in this case maybe is related to the C60 layer, that we can see that there is the presence of inhomogeneities in some places, for example, in this region, in the right-hand side, where you can see that there's even the presence of some holes. And of course, this leads to degradation of the photovoltaic performance of the devices. So we need to already know that we need to optimize the process deposition of the C60 layer. In the terms of optical properties, you have a very good transparency, which is higher than almost reaching 70%, the ABT value, even if the ultraviolet filtering is relatively low. We only achieve about 95% of absorption. So we need to have to increase the ultraviolet absorption in this region. But we think that this will not be critical. I think we will be able to do this just by playing with the thickness of the xenon phosphide layer. As the optoelectronic characterization of the devices, for the characterization, we have worked with an ultraviolet intensified solar simulator, because one of the problems that we have for this kind of devices with the standard solar simulations is that in standard solar simulators, the ultraviolet spectral region is not well reproduced from the spectral region on the radiation of the solar sun. So we have been able to demonstrate the first ultraviolet selective solar cell prototypes that have well, still are non-optimum devices, of course, with moderate with a low efficiency of almost 0.5%, but we have a very good transparency, 69%. And what's also very interesting is the optical quality. Here you can see a photographic image of the solar cell that is just on top of the IREG logo, and as you can see, we can not recognize the presence of the cell. So it's really a transparent solar cell without any coloring effect. In fact, this is one of the best reported oxide up to now oxide-based, ultraviolet selective oxide-based devices in terms of what we call the light utilization efficiency, which is just the product of the photoconversion efficiency and the visible transparency. We are working now in the optimization of these first proof of concept devices to increase the efficiency essentially. For this, we are working the optimization of the composition of the absorber layer. So we might reduce a bit the band gap to increase the efficiency. And also we need to improve the crystalline quality of the layers to increase the grain size. We already know that we need to optimize the deposition of the C60 electron transport layer to optimize the uniformity. And we are also thinking, we're also working in the replacement of nickel oxide as a whole transport layer, because as you can see, there's a problem we already know from nickel oxide, is that there is a strong discontinuity in the band gap structure between nickel oxide and xenon sulfide, and this leads to a strong limitation of the open circuit voltage that can be achieved with these devices. So we are working in the identification of alternative optimal whole transport layers. Essentially, we are working with 3 candidates with molybdenum oxide, molybdenum sulfide, or rubren. In terms of multifunctional UV coatings, we're also working in the chalcogenides approach. In this case, essentially, these are zinc sulfoselenide layers that are deposited on FTO substrate. Well, these layers are synthesized by sequential process where the metal zinc is sputtered, that's deposited by sputtering, and then there's a reactive annealing in H2S and H2 selenium, H2Se atmospheres. We observed there was a first problem is that in these conditions, the selenium was able to react to the surface of the FTO and degraded the optical quality of the layer. So for this, we had to include an ICO, an indium zinc oxide layer, to protect the FTO. This we have seen that has a problem that is determines a yellowish color, and you can see in the photographic image in the slide. So we know that we need to solve this problem of the yellowish color, and we think that for this, what we will do is to replace the ICO by a nickel oxide layer, for example. But what we have seen is that we can control very well the band gap, controlling the sulfur to selenium ratio. In this case, corresponds to a layer with a 3 electron volt band gap. And this allows us to obtain the layers with a very good ultraviolet filtering, which is filtering almost all radiation below 380 nanometers wavelengths. An important issue in this case for making the solar cells is to dope in a suitable way both the P and N type, the zinc sulfoselenide layers, trying to make an homojunction. In the case of P type, we are working essentially with lithium, but most interesting is for the N type, what we have very good reduction of resistance using germanium, copper, or tin. So these are essentially the results that are achieved at this moment. Going to the main conclusions, well, I have not spoken about the activities in the other work packages, but we have had a very strong activity in the definition of the requirements and the specifications of the glazing system proposed for Tech4Wind. And this has implied a strong analysis of the standards and regulations. We have had to work with the regulations corresponding to different climatic regions, because the standards, the specifications that a window has to fulfill depend very much of the climatic region. So this has led us to the proposal to propose designs of the Tech4Wind window, one that would be valid for hot weather conditions. This is the simplest one. But for we know that for temperate or cold weather conditions, we need to introduce a gap in the window structure to be able to obtain the thermal insulation level that is required. So it would mean a more complex, like a double glazing structure. We have also implemented the modeling tools for the electro-optical modeling of the window device structure, and this is important to optimize the standard device architecture, because we have to put a very high number of layers, but at the end, all these layers have to not to compromise the level of transparency. We have to keep with this transparency level higher than 60%. As I commented, we have done a very strong work in the development of the infrared selective devices with the identification of polymers compatible with the KPIs and the demonstration of PERS or OPV operative devices, where we have two potential candidates that allow us to have very good visible transparency at the level of 71% with an efficiency that is in the level of 6%. On the other case, we can reduce the transparency to 58%, but still we have a very promising efficiency higher than the expected value. This case is 8%. In any case, what's important is that these are results that are done without implemented back reflector, the internal back reflector. So implementation of the internal back reflector, we will expect an improvement in the efficiency in the level of a relative improvement about 20%. So this would allow, in the case of the higher transparency approach, allowing 71% transparency, to recover and to reach the 7.5% efficiency that is targeted in the project. And for the ultraviolet multifunctional coatings, we have already demonstrated zinc oxide and zinc sulfoselenide layers that have a very good behavior as ultraviolet filters with an absorption higher than 99%. And we have also demonstrated first proof of concepts of zinc oxosulfide-based ultraviolet selective solar cells. So this is the presentation, and thank you very much for your attention. Okay.
Yeah,
so
thank you very much, Alejandro. I'm making Victor a presenter now.
Okay.
And just during the transition, Alejandro, I wanted to ask I think you said in the beginning of your presentation, your ambition is to replace basically most of the window in existing buildings. But your technology, is it going to work for the opening windows or only the ones which we can't open? I'm just thinking of the cabling and all those electrical.
The idea is to work in the standard windows, in the normal windows in houses, open windows. The idea is not to restrict the device design to essentially glass facades, but really just to replace, because the idea is trying to not to limit ourselves to prestigious buildings where design is a very strong impact, but trying to go to a huge potential market, which is normal houses. I would say that's the target. Okay, there are a lot of challenges, of course, because there's also the issue of the cabling and how to integrate all the electronics in the window frame, essentially. But it's not so difficult. And in fact, I think that Victor will show some things that are very close with this. And in this case, is another technology that is the similar solutions that are being, and in fact, are very close to commercial exploitation.
Okay, perfect. Thanks very much. And I'd like to remind as well all the attendees that they can ask questions at any moment. And even if we are running a bit late in this session, we'll be able to answer all the questions even after the session offline. So really feel free to ask your questions. We will record everything and all the speakers are going to get back to you at the end of the session. So the floor is yours, Victor, and we can see your slide.
Okay, perfect. You listen me, no? Okay. Well, thank you very much. Good afternoon. I'm Victor Izquierdo from Spain. I'm working as senior researcher at Catalonia Energy Research Institute, and I'm the coordinator from the Solar Wind project. Okay. Well, the motivation of this project is relative to the new regulations from the European, well, the European regulations that push to generate building no architectural sector to develop more energy efficiency buildings and try to reach near zero energy buildings. Okay, the standard technologies, the normal technology that is applied currently is focused in implement photovoltaics elements in the roof or in the facade. And the idea of the motivation of this project is try to use the windows region that there are in the facade of the buildings, okay, and generate a new BIPV windows that have a higher transparency and no intrusive elements. In the frame that is fine at this project is in the frame of the Horizon 2020, in particular in the Fast Track Innovation Program. That the objective of this program is push some relative mature ideas to a final product that commercialize it in 3 years. Okay, that this is normally a short projects that are intervals that start in intervals very higher in relative 8 order of the 8. Okay, and finally generate a product that is commercialized in 3 years. Well, the objective of this project is, the main objective is generate these new solutions, these new windows that have a colorless effect and through non-intrusive transparent BIPV windows in only 2 years. The state of art that we have currently is that some technology that is patented from FISI, that we have some prototypes based in silicon technology and using some coatings for convert the light to the visible light to infrared or near infrared that have some limitations that we try to solve in this project. The first is this one. This is the specific objectives that we have. Is make a truly transparent and visual non-intrusive windows. Generate some filter that block the infrared, that is improve the comfort inside of the buildings. The third is that make easy integration. The idea is that generate standard windows that are compatible with a standard Windows that exists currently now, and only don't require two modification of the facade. It's directly replace all windows for these new windows. The next objective is focused in the generation. We try to generate 30 watts per meter square of windows. The next is the generate a product that have a short payback below to 4 years, and finally that demonstrate or generate a product that have a lifetime equivalent to a standard Windows, that is more than 20 years. The consortium is 4 partners that are defined in 3 different countries, in Netherlands, Austria, and Spain. They is formed for 3 companies. FISI, that is a partner that have expertise in smart windows. Unplugged is a company that have expertise in generation or manufacturing a customized photovoltaic solutions. In the third industrial partner is Acciona, that is a leader construction company. And finally, there are one research center, that is IDEC, that coordinate the project and provide the expertise in characterization of the materials and the implementation of process monitoring. A more detailed description is you can find in this slide. This is the main role that have IDEC, or the expertise that have IDEC, that we generate from the fundamental characterization for identifying what is the properties of the material, identifying a potential process monitoring technology or techniques or methods, and identifying quality controls indicators that will be potentially implemented in the industry. Develop or design optical systems for perform inspection tools in the industry, and finally manufacturing a prototyping for evaluate in pilot lines and industrial pilot lines. The next partner, the FISI, is the company, it's a Netherlands company that have the knowledge about these windows, these photovoltaic windows. He has patented the technology and currently have a prototypes based in silicon and exotic coating. The idea is with these windows generate enough energy for a local storage, for provide power for sensors, for interconnect elements, 3-party elements, and IoT systems. And the main objective is that produce some system that we can detect that is a photovoltaic windows. It's make a windows that have the same performance that the standard windows. Okay. The next partner is Unplugged. The main background is that he have the tools and the methodologies for implement a customized photovoltaics modules. The idea is that he have a high flexibility manufacturing, and he can produce different size and modify the modules in order to coupling well with the final solution or final application of these modules. And the last partner is Acciona, that is a construction company, and he have a strong background in the design, construction, and managing buildings and civil infrastructures. And additionally, he have facilities for testing and validating new materials and new concepts for building applications. Okay, here is a picture from the test cell that he has for evaluate the properties of the construction elements. Well, the technology principle of the product is this one. This is some cross section of the window. And there are 3 main elements that are developed for FISI, and in this project we try to optimize and modify for obtain this 30 watts for meter square. The first element is a luminescent layer that we can introduce here. Is a laminated glass that introduces this new some coating that convert the near infrared light in some narrow emission. Here I show. This is the sun spectrum, and this gray region is the region that absorbs the light. If you see that it's outside or it's far to the region that the eye detect the light, mainly the main region is this one. This makes that the system is no intrusive in terms of visibility, and all the energy absorbed in this region is remitted in this narrow region. The idea is generate photovoltaic elements or modules optimized for absorb this region. This elements is placed in here in the frame of the window, and we need to optimize for have a higher absorption in this region. This is outside of the region of the silicon technology, for example. Additionally, there are another effect that the idea of laminate this coating is that this provide additional effect is that concentrate the light and make some type of the optical guide that move or canalize transport the light to the edges. This introduce some concentration effect, providing a high light intensity in the frames. Okay. Finally, the idea is that generate these windows without any special architecture. This can be compatible with a standard windows frames. That this means that we can adapt the facades that we have now to this. Well, it's adapt the window to the facades that exist in the buildings. Well, the roadmap of the project is this one. The project is starting the last year. Now we are in the middle of the project. We are in this point, exactly in the middle. The first part of the project is focused in the optimization and technology coupling, because we need to adapt the photovoltaics elements to the glass and the coatings existing in the BIPV. Additional, we need to develop a process monitoring technology for help to the reproducibility in the manufacturing of these modules. This is the 3 lines that we have here. Now starting the second part. We are in the half of the second part of the project, that is implementation of a functional prototyping. Okay, and starting to the implementation of manufacturing of these photovoltaic modules based in copper, indium, gallium, selenide technology, and starting to the test in controlled conditions. And in the last part of the project is finally the focusing in the validation of the technology in real conditions. This means that finally it's produce enough photovoltaic panels for implement several meters of windows around to the 30 meters square, and testing it and certificate, and finally make a final test in a demo site place. Focus in each part, or enter more deeper in each part. Here we show the preliminary results that we have in the project. Now with the photovoltaic module optimization in this near infrared, we are modifying the architecture of the copper, indium, gallium, selenide based modules in order to improve the quantum efficiency in this region. The objective is achieved around to 15%. Now we assume this target. Additionally, it is necessary to readapt the interconnection of the module for minimize the losses for the interconnection of the module. And this we are working in the monolithic interconnection. This is a technology developed for some plugins, but based in monoscribing and monoscribing process, and using interconnection of the cells based in conductive inks, and the printing of the conductive ink. The second part is the process monitoring for give support to the fabrication of these modules. and he is involved with IREC. And in this part, we are developing the methodologies, identifying the main quality controls indicators. The tool that we implemented here is interesting. It's required that we make inline process monitoring for follow the on time the production of the devices. And this means that we need to generate mapping analysis in short times. Here we optimize the process monitoring tool for achieve measurements lower to 10 seconds and provide enough information for identifying what is the problem of the manufacturing of the panels. The part of the window design is managed for FISI, and he has two sub-tasks. That the first is that the luminescent coating optimization. For this, FISI have modifying the current the previous photoluminescence coating for a new coating more cheaper, based in manganese ion, and currently he achieved transmittance around to 60%. And no and colorless properties, and this means that we obtain a very low intrusive effects in the windows. And this technology has been developed for implement glasses to the 1 meter square. In terms of the Windows structural and electronic design subtask, FISI has working in the implement all the technology and the electrical elements and the coupling of the glass with the modules in a standard frames, Windows frames. Here you have a picture. This is a standard frame, Windows frame, that is working in the technology how coupling these glasses with the modules and introduce in these frames, and implement inside of the frame all the electrical components required for the extraction of the energy from the window. The next task that is focused in the prototype implementation, and this is a task that currently we are involved with, is that coupling the modules, the stripe modules developed for some plugins. Sorry, this is the stripes of the module that is currently used. These modules have a power out around to 2.8 watts per meter square, and these modules has been implemented in the edge of these laminated glasses. Here in the middle, we have the luminescence coating developed by FISI, and generate these glasses that with the dimensions required for the project is around to 1 meter square, and with the properties required is a transmittance higher to 60% and colorless properties. And additionally, the lamination and the coupling of the glasses now is working for achieve a higher improve the concentration light in the edges with a factor of 10. Finally, is that implemented these glasses inside of the frame and coupling with all the electronics connections, and implement the first window. Here you have a picture of the first prototype, that the functional prototype that was testing, that we preliminary testing, we obtain a 1.1 watt per meter square, but you take in account that these conditions is without any control, is measuring directly with the sun, but without control the radiation and without align well. It's the good thing of this first prototype, allowing us to identify the first, the main power losses mechanism, and identify that the main loss mechanism is linked with the coupling of the light between the glass and the photovoltaic module. And we are working now in solve this problem. And these first prototypings that don't achieve the 30 watts for a meter square, but we are starting to evaluate this in the Acciona test cell building. The idea from here is evaluate what is the comfort effects and what is the properties of these modules, what is the stability in real conditions. And here we are evaluated we include different sensors, the thermal sensor, the light sensors, the electrical sensors, for try to follow how what is the behavior of these windows in real conditions, in days that have sun, when it's cloudy days, this type of a thing. And with this, we recover this information for evaluate the efficiency of these windows. The idea is testing the prototypes during 6 months and provide information about what is the properties of this product and what is the limitations and what is the things that we need to optimize. And now I want to show we want to jump to what is the next actions that we need to do in the project for achieve the final product. Now we are here in the middle, and in terms of the photovoltaic mode of prefabrication, now we need to implement the new near infrared photovoltaic concept in the pillar line. The previous modules was manufacturing, but no using a standard pilot line. Is implemented in a special. It's a special manufacturing, and when we introduce the manufacturing of these modules in the pillar line, we expect to have a higher homogeneity, and this means that improve the quality or the power out of these strides. The second part is that we are always the prototype implementation. The idea here is improve the coupling between the light providing from the glass guide with the photovoltaic modules. This now we are working to try to improve this one, and we expect to increase the power obtained from this element to the one part that we obtain currently. I remember you that is in not controlled conditions. It's expected that in controlled conditions in one sun irradiation, probably this is higher. To other 30 watts per meter square. And the next action is related to the testing in controlled conditions and certificate of the windows. This is now we are starting with this first prototype. The idea is evaluate and second generation of prototypes that we achieve in the next month, and evaluate this and certificate for the possibility to the manufacturing of this project, this product. And the next is that next action is the manufacturing of 16 windows from 2 meters square for testing it in real conditions. This is a task mainly for the PC, and manufacturing these 16 windows that is equivalent to a 32 meters square for evaluate a demo site. This is the last task is that implement these windows in a real real building. This is a building from IREC, from the IREC Institute, and the idea is install these windows in different places with a different light conditions. The idea is testing in real conditions under different light illuminations. This part is a region that have a clear region that we obtain a very sunny surface. This is a part that have some limitations for shadowing with another building. And this part is a part that is orientated, it's not a correct orientation with the sun. This is orientated in northeast direction. Well, as conclusions is that now we implement all the steps required for obtaining a first functional prototypes. This means that we are developing photovoltaics modules optimized for a near infrared absorption. We are implementing a coating that provides us a dome conversion effect that allows to obtain energy in very narrow region without introduce any effect in the vision. And finally, we are developing the structural and electrical elements for integrate all these elements in a real or standard frame, window frame. Okay. And now we attend these first functional prototypes, and we are identifying the main loss mechanisms that is allowing us to improve the different parts for try to achieve this 30 watts per meter square that finally is the objective of this project. The perspective is in the next month we have a second generation of the windows that achieve these values of power without degrading the transmittance or the color of the windows. Well, thank you very much for your attention, and thank you if you have some questions.
Yes, Victor, I will give control to Frédéric, and Frédéric actually has a question for you in the meantime.
Sorry, I don't see.
So he wrote the question in the chat, so I will read that. It's how is defined the M2? Is the window aperture or the area by the NIR-PV? I think Frédéric will be able to ask your question much better directly.
Okay, is Frédéric, you want to know the area of the window?
No. The question was very simple. When you report the power per meter square, I was wondering whether the meter square is coming from the aperture of the window or just the meter square of the near infrared PVH.
It's the total window. The idea is the total window. Taking account is efficient. The idea is that it's a product. Is that you have 1 meter of hole that you introduce this window. You have in this meter this 30 watts per meter square.
Yeah, so this is defined by the dome conversion area.
Exactly, yes. For this is important the down conversion effect. Here the idea is not have an intrusive effect. This means that reduce a lot the absorption of the light finally, because you don't see any or you see reduction a little of the intensity of the light. But it's so that we need to this small area, this small light absorption, we need to optimize a lot, and with this achieve the 30 watts per meter square.
Okay, got it. Thank you.
And perhaps since we are on questions, I see we have a question as well for Bismart. Laure Emmanuel, are you still with us? Maybe no. Then we will handle this question at the end of the session in case Laure Emmanuel is back with us. So you can go ahead, I think, Eric, and we can see your screen.
Okay, thank you. Okay, whoops, what I did wrong. Okay, so you see my screen, I put full screen. Okay, so just to start, I would like to thank you, Alejandro, and Sustainable Places for giving the opportunity to Impressive to present well, what is the aim of that project, and also some of the results that we got for the last year and a half. So my name is Frédéric Sauvage. I'm researcher at the CNRS. I'm heading here a group in photovoltaics and photocatalysis, and I'm the coordinator of the Impressive project. So Impressive means groundbreaking tandem of transparent dye-sensitized and perovskite solar cells. It's a very small also projects in terms of numbers of participants. We are 4 public entities, I would say, the CNRS, the University of Torino, the École Polytechnique Fédérale de Lausanne in Switzerland, and the University of Rome.
And on the other side, we have 3 SMEs that are here: Edge Glass, Euro Quality, and Smart Green Scan. So the core idea of Impressive is relatively simple in the implementation. On the one hand, we are separately developing a selective UV perovskite solar cell, so to convert the UV part of the sunlight into electricity. In parallel, we have the development of also a selective near-infrared converter. But for that aspect, we decided to work on the dye-sensitized solar cell technology. So we are working on 2 types of technologies, which is more or less the same approach that what has been presented by Alejandro. And then separately, we try to increase the average visible transmittance of the 2 separate devices, and then we go for the 4-terminal tandem solar cells, which normally should add the properties in terms of performances of the 2 separate devices. So in terms of KPIs, so the objective here is to develop a perovskite solar cell which can get 6% power conversion efficiency with an AVT, available visible transmittance, of 75%. For the near-infrared dye-sensitized solar cell, we've been also very optimistic, I would say, to the one end. So we target 75% also AVT with a power conversion efficiency of 8%. And the final objectives will be to have a 40 tandem solar cells which convert both UV and near-infrared with a power conversion efficiency of 14% and an AVT of 55%. So Impressive is what? Impressive is a project which has a basic science and a technological balance work program. So the core unit is here, the work package 2 and work package 3. So this is a separate development of the UV perovskite solar cell and the separate development of the near-infrared dye-sensitized solar cell. We have a transversal activity here, which is the work package 5, which aims at the stability assessment of the separate devices and of the tandem devices. And we also, let's say, take advantage of a characterization toolbox that we have here in the CNRS and also at EPFL in terms of time resolved spectroscopies, or in terms of X-ray diffraction under light, X-ray diffraction under humidity, X-ray diffraction under temperature. We can combine all those parameters together in order to get a real assessment about how stable are the materials inside the devices. Then work package 2 and work package 3 are together within the work package 4, which is the design and the assembly and the characterization of the transparent tandem cells. So then we try to combine them into, let's say, a tandem cell which the size is a few centimeters square. And then once this is validated, we go, and this is the main part of the 3rd year of the project. We go for the upscaling in terms of materials, but also upscaling in terms of the size of the modules, for which we have 2 steps development. A first step is 15 by 15 centimeters square module, and then the second step is very close to A4 format, which is 20 by 30 square centimeter. And so this is the core, the real core of Impressive project. And then we have a life cycle assessment work package, life cycle cost evaluation, dissemination communication activities, work package 1 here in vertical, which is innovation potential and business strategy, and of course the project management. So again, in terms of KPIs, the final goal for us is to reach 14% power conversion efficiency with the tandem devices and 55% AVT, which is, as Alejandro said, this is already a very transparent technology. In Impressive, we also need to define, not we also need, but we are defining a clear roadmap strategy for Impressive and also for the post-Impressive projects in order to level up the TRL. So actually we start with a TRL of 3, so we're very low compared to all the projects that has been presented at the beginning of this workshop. So we start at 3, and we will end up, if everything goes okay, at TRL 5. And the final idea is not only doing Impressive, but it's also to think about the post-Impressive project to bring the technology to the market And then if all milestones are passed, we can target an industrialization step horizon 2030. Okay, so in this presentation, this is low TRL, so there is a little bit of science, and I decided to present most of the presentation related to the dye-sensitized solar cell for the near-infrared conversion. So most of you knows what is a DSSC. So a DSSC really look like an electrochemical devices. This is the only photovoltaic devices for which the principle relies on electrochemical processes. So it looks like a battery, in fact. It has two electrodes separated by an electrolyte, which can be liquid or solid. In our case, it's a liquid electrolyte. And everything happens here in the photoanode, where you have nanoparticles of the anatase TiO2 nanocrystals, which are sensitized by an absorber, which can be an organic absorber or organometallic absorber, for which the role is to absorb the light, separate the carriers, if the LUMO and HOMO levels of the dye are well aligned with TiO2 and with the redox couple, we should have a separation of the carriers, so electron injection into the conduction band of TiO2. And then if I'm taking the example of the ruthenium complexes, this ruthenium complex will be oxidized, ruthenium 2 to ruthenium 3+, and then it will be regenerated by whole donation to the redox mediator. So typically the redox mediator are based on iodine iodide, or often now based on cobalt polypyridyl complexes. So in the field, thousands of absorbers have been developed. It's very interesting because depending on the dye structure, you can color the devices at the coloration you wish, meaning that you can make it red, purple, blue, yellow, green, orange, or black, if it is really panchromatic dye. So this is, on that sense, a monochromatic selective absorption devices, which is very important for BIPV in terms of aesthetic. It can be different coloration. It can be also semi-transparent to transparent devices. Looking at the state of the art, I would say, in the field of dye solar cell, mainly the work in research were devoted to improve the efficiencies. Today, the efficiency of dye solar cell is 14.2%. And typically, to improve the efficiency, one would develop a dye which absorb as much photons as possible, so panchromatic absorption and high molar extension coefficient. And secondly, you need to reduce as much as possible energy losses, which are coming typically from a mismatch from energy alignments between the redox mediator and the HOMO level of the dye, or between the conduction band edge of the titania and the LUMO level of the dye. But not only, because when the electrons are in titania, they can also recombine. So one would try to avoid what we call the non-geminate recombination processes, which are through the ox form of the redox mediator, or the geminate recombination processes, which are going through the oxidized dye. So typically, this is the state of the art. Many works devoted to dye development, many work devoted to nanostructure these electrodes of anatase TiO2, and many work are devoted actually to different redox mediator. Improving efficiencies and improving stability, of course, and improving stability mainly rely on work related to the electrolyte. Okay. So the idea of Impressive was to try to develop a new concept, because indeed dye solar cell can be monochromatic, but monochromatic in the visible part of the light. Why not only visible part of the light, and why not going to the UV or to the near infrared selective absorbers? And that was the concept, or the starting concept, I would say, of Impressive. So making a transparent dye solar cell is possible. The choice was whether we go for the UV or the near infrared. So it's very easy to understand why we went to the near infrared and not the UV. The first is because UV takes into consideration only 4 or 5% of the solar spectrum. But not only that, it's because also in the UV, the glass and the TCO are strongly absorbers. TiO2 is a very good photocatalyst, as all of you know. So it absorbs very efficiently the UV part of the light, and unfortunately, I would say the solvent and the electrolyte components are very strong also UV filters or UV absorbers. So if we want to develop a UV dye solar cell, I think that the efficiency will be extremely close to zero, and the stability will be also very poor, meaning that you will excite directly the bang gap of titania, and then the hole that are located in the titania are very oxidized. So near infrared takes about 46% of the solar spectrum, and the only drawback for a dye solar cell in the near infrared part is that the free carriers in the titania absorbs at about 1000 nanometer and above 1000 nanometers, so which will reduce part of the transmitting light in this region. So the open window there is around 750 to 1000 nanometer, I would say, for dye solar cell. So we've been working on this topic since 2012, so it makes now 8 years, in strong collaboration with our friends at the University of Torino. We started from this very nice blue color squarine dye that we developed, back in 2011, and we published in 2012. And then we work on molecular engineering, so modifying the central unit of the squarine, or modifying the lateral unit of the squarine in order to redshift the absorption from 620 to, let's say, 800 nanometer. This has been a very long road, going back and forth between our two groups, and this was the work of Vittoria Novelli in my group. So we were synthesizing in collaboration with Torino new dyes, and going back and forth between syntheses and devices was for a couple of years delivering always bad news. We spent time in syntheses, but efficiencies-wise was always in the range of 0.1, 0.2, 0.3% normal. And then came this very interesting dye. This is a polymethyl cyanide dye. So cyanide dyes are very interesting as molecules that are very luminescent in the near infrared. So this is the structure of what we call the VG20. It absorbs at 830 nanometer. And this is here the UVV's absorption spectrum of the dye in solution. This is the emission, very sharp emission, also in the near infrared part, and this is the photopic response of the retina eyes, human eyes. Okay, and where it's beautiful is that the main absorption band, the S0 S1 transition, singlet to singlet transitions are very, very strong in the near infrared, and often happens in many dyes. We always have a contribution in the blue, but these very small S0 SN transitions in the blue are just a little bit apart from the photopic response. So in solution, what you will see is this green color. It is a green dye which has a photoluminescence, quantum yield of 47%, but it has a very, very high molar extension coefficient, 150,000 liter per mole per centimeter. Vertical excitation is very close to the band gap value, 837 nanometers. So that's the reason why the molar extension coefficient is that strong. You do see a green coloration in solution that you will not see if the cuvette is a few tens of micrometer thickness. This is because of the molar extension coefficient. In terms of energetics, this dye is interesting because when you reduce the band gap of the absorber, often you start to have problems either for the injection, either for the dye regeneration. And this is really what limits the near infrared dye solar cell, is that you comes in competition between injection and regeneration. So actually, this is the HOMO levels that can be regenerated by iodine iodide redox couple. This is the LUMO level, which is at minus 0.4 volt versus NHE, which is right at the alignment of the conduction band edge of the anatase TiO2 nanocrystals. We did a little bit of science about those molecules, especially in terms of time-resolved spectroscopies. So here is time-resolved photoluminescence, which showed that the excited state lifetime of those kind of molecules are very short, 400 picoseconds. By comparison, a perovskite solar cell is microsecond timescale, or a ruthenium polypyridyl complexes, which is the standard for dye solar cell, is about 10 nanoseconds. Here we have 400 picoseconds, which has also been confirmed by another technique, which is the transient absorption spectroscopy, showing exactly the same results, meaning that the excited state lifetime is very, very short, and then you really need to prompt the electron injection before the dye decays itself and gives luminescence in the devices. Dye typically in solution often are interacting between each other, which forms either head-to-tail aggregations, which is G aggregates, or either head-to-head aggregation, which is H aggregation. In solution, we have actually no hints that VG20 is a dye that tends to aggregate. But unfortunately, VG20 is a dye that tends to very strongly aggregate when it comes into the self-assembled monolayer on the nanocrystals of the anatase. There is different means to avoid this aggregation, and the typical one is using this deaggregating agent, that is the quinodeoxycholic acid, so which we call CDCA. So if you sensitize the nanocrystals without the aggregating agent, this is what it will turn out. You will not only have this very nice solution shape of dye, or I will not come back, of the dye in solution, but you will have a very broad absorption band with contribution also from the near infrared. So we have some G aggregates here, but very strong contributions of 8 aggregation, which makes the coloration of the devices really green. So it's not green because of the monomer, it's green because of the H aggregates that are formed as a self-assembled monolayer. And once you start to introduce this CDCA in the process of the sensitization, then you break the aggregates, and you turns out to have a photoanode which turns from green to something which is colorless. Okay, this is pictures also to show that when you have aggregation, you also are quenching all the photophysical properties of the dye, and then you avoid injection, you avoid regeneration, and you simply decay the dye after excitation. So how important is the aggregation for the device performance? We've been working on CDCA, but we also worked on the molecular engineering. So this is typically how it happens with H aggregations. Then you have lateral interactions, very strong lateral interactions between the dye, especially when this is electron-rich central units. And the general idea was to try to break this self-assembled geometry with long alkyl chain here. So we've synthesized short, mid, and long alkyl chain from C2 to C16. And this is what it turns out. So when you make a long alkyl chain in terms of devices, you will see first, of course, it becomes more transparent, but secondly, you improve the photocurrent and you also increase the cell photovoltaic. Increasing the side alkyl chain also tends to increase the electron lifetime, which means that it reduces the non-geminate recombination process inside the devices. So we have a better charge collection efficiency of the carriers, and it slightly modify the cell capacitance, which means that it slightly modify the self-assembled monolayer geometry. So in terms of performances for the near-infrared dye solar cell, the best that we can get actually is 3.1% efficiency with sensitizing at very low temperatures and for a week. Typically, this was a process that we published a couple of years ago with ruthenium dyes, and it works also perfectly with organic dyes and with the cyanine dye also. So we can improve the efficiency at low temperature, and it tends to also reduces the amount of aggregation. We can reach up to 60% IPC at 860 nanometer. And this is also to demonstrate here that the low sensitization temperature affords to increase the electron lifetime. So to reduce the internal non-geminate recombination processes. Another question is 3.1%. This is relatively low, and we would like to increase to 8%, which is one of the targets of the project. We try to understand exactly which steps are limiting actually the performance of this dye. So this is typically the photophysical scheme of the dye solar cell. You excite, it injects, so you have an injection rate, but this injection is in competition with the excited state lifetime, which can be problematic, knowing that The excited state lifetime is only 400 picoseconds in solution, but I should also say that when it's in the self-assembled monolayer, it's more 50 picoseconds than 400 picoseconds. Then you have introduced this electron in titania. You need to regenerate your die, which is oxidized now. So you have the regeneration through the redox couple, but this kinetics comes also in competition with a non-wish processes, that is the geminate recombination process, which means that the electron in titania recombine with the oxidized die. This is something which can happen. And typically, to try to better inside those two processes, we use pump probe transient absorption spectroscopy. So we have a very nice setup with a straight camera, which affords first, when you include the redox couple in the electrolyte, to see at which speed the electron, the hole from the radical dication is transferred to the redox couple. So this is VG20 plus point, because this is a radical kinetic. So you will see this is the spectral fingerprint of the radical cation, and this is how fast is this all transferred to the redox couple. So, and here you have the ground state bleaching, so you do see some noise, and then you have the bleaching, which means that the ground state is not absorbing anymore because it is oxidized already. So typically from this, you can deduce the speed of this all transfer to the redox mediator, which is in the range of, we have two components, which we attribute to the monomer and the aggregates. One is 1 microsecond, the other one is 20 microseconds. And if you want to measure the geminate recombination, which is the enriched process, then you use exactly the same procedure and techniques, except that you remove the redox couple to block or to anneal this reaction. And then if you look at carefully the scale, you will see that you go from few microseconds to few milliseconds. And this is the geminate recombination process, which takes in a couple of milliseconds. So if you want to determine the regeneration quantum yield, then it's very simple, the ratio between those two numbers, I will say, and one can easily see that this is 1,000 times faster than this. So the regeneration of the die is 99.9%. So everything goes very well for generation. Now what happens for the injection? And then the scheme is more complicated. I'm not going to the details of the transient absorption spectrum, but here you have still the dication. Here you have the ground state bleaching of the aggregates, the ground state bleaching of the monomer, and here it corresponds to the emission of the dye. So we carefully analyzed with an injecting TiO2 to know how fast is the injection, and to a non-injecting zirconium dioxide to block this reaction and to see how fast it decays. One can see that they are very similar, and this is very unusual for a dye solar cell. They are very similar, and if you look carefully to the decays and you analyze all the decays, we spend many months on this, one will find that we have another process which is very harmful for the devices. It's not the injection, but this is energy transfer from the monomer to the aggregates. The aggregates are very problematic for the devices here. So you have an energy transfer from the monomer to the aggregates, which is in 2 picoseconds. And the dye decay within 50 picoseconds. And the injection from the monomer is in 8 picoseconds. It means that this is faster to energy transfer to the aggregates than injecting into titania. And then from the aggregates, you can inject into titania, but in 32 picoseconds. If you calculate the injection, the total injection yield of the system, one will find that injection is 55% yield. And this is in very good consistency with the IPC, which was showing a maximum of 60. You cannot go above 55, 60% IPC with that low injection yield. I will end up here with the science, and I will summarize where we are actually with Impressive and give some take-home messages, I will say, from the project. For the near-infrared dye solar cell, actually, our main problems is really the aggregation, which reduces AVT and reduces the power conversion efficiency of the devices. However, either with iodine iodide redox couple, which gives a slightly orange coloration, or with a sulfur-based redox couples, especially with these devices, we've been able to reach an AVT of 82%, which is really, really excellent. But unfortunately, the PC is relatively low, 3.1%. We got 4%, but I'm not presenting this because we have a patent under filing. We still an AVT above 75%. Where we need to work is to increase the PC and also to make it a little bit more neutral coloration, as Alejandro was pointing out very precisely in his presentation. So we need to develop a dye which has not this shape here, which is related to the H aggregation still. So we have to shift a little bit by 20-30 nanometer the singlet transition of the dye in order to make it completely color neutral, because this sulfur-based redox photo is totally transparent and colorless. I was discussing the UV, but for a matter of time, I'm not developing the UV part. But UV are made of perovskite. We've been working a lot with the methyl ammonium lead bromide system, which gives this yellowish coloration. Actually, the AVT of the device is 55%. But the power conversion efficiency is more than 8% actually on mini modules, which is really, really excellent. It looks like we have a complementary set of experiments with Tech4Win. You are very strong with the near infrared and less with the UV. In our case, this is totally the opposite. We are good for the UV, but we still have to work for the near infrared. So maybe we should make a tech for impressive or something like this. Anyway, here we have many solutions to make it more color neutral, especially if we replace a little bit of bromide by the chloride. You will improve the band gap of the materials to 3 electron volt, and you will make it to 2.8 electron volt, and you will make it more color neutral. But unfortunately, that's going to increase, the AVT, but we know already that it's going to decrease the power conversion efficiency down to, let's say, 5%. Okay, I'm finishing here. Of course, I would like again to thanks for your first your attention, and second for the opportunity to give a little space to impressive projects.
Okay, thank you very much, Frederic, for this nice presentation. And you're right, very complimenting very much Tech4Win, which in fact I forgot to comment. Both projects are for the same call, from the same.
Yeah, we are from the same call. We are already in parallel.
Yeah, really true. Okay, Regis, I don't know if there's time of any kind of question. We are strongly late in relation to the schedule. I'm sorry about this. No, I think there was a lot of information to be given about the different projects. I think that
indeed, and very interesting presentations from all the speakers. Thank you very much to all of you. I think we do have one question for the Bismarck project, so we go back a bit in the agenda. So it's a question for you, Laure Emmanuel. The question is, are you considering sustainability impacts related to the different coloring processes? So that's the first question. And then the second one is, how colored glass impact on PV efficiency?
Thanks for this question. So for the first one, it's true that we have not considered sustainability impact. So we have not done LCA assessment, and we focused a lot first on the deal between finding the good aesthetic and keeping the good efficiency. And we focused also on the cost aspect, but this is something that we absolutely have to consider. We have not yet done it clearly. And perhaps the second question is a bit more easy to answer. So how is the impact of the color on the PV efficiency? So of course, when you apply these different filters in front of the solar cells, you decrease the efficiency. But all the technological innovation in this development are to be able to design these different color filters in order to select some wavelengths to optimize the efficiency of the cell. And so the strategy here is to try to find pigments or dyes which are transparent in the infrared, so that the infrared light goes through the solar cells, and the visible and UV light is used to make the color, and especially the white color. So then the loss in efficiency vary a bit different depending on the colors and the pigments properties. But we can see that, for example, for white, which is worse in terms of efficiency lost, is about 30%. And if we go for terracotta, we can go to 15%. But again, there is no defined efficiency because it's always a balance between the aesthetic we want and the efficiency, because sometimes we don't want to see at all the solar cells, and then we will lose a bit more efficiency. And sometimes we accept to see a bit the solar cells, and then we increase the efficiency. But here in this question, I think it's also bring a very important point is what is the reference we have that I mentioned also during my presentation. And I think it's very important when we are talking about solar panels for a building facade, not to compare with a standard PV modules, which is very difficult on an architectural point of view to be integrated. And so, in fact, the reference is not the standard PV module, the reference is a building element which is non-active. And then the question of efficiency is also tackled differently. We only gain efficiency. We are not losing efficiency. And it's why also we propose to try to name differently this product, like energy positive glazing, just to get rid of the reference of the PV module. It is a PV module, but it is a PV module which is not developed for the same application. And then the reference should be different because also the cost calculation is very different, as we have seen in many talks. It's not about only cost of electricity, it's also because it replaces other building elements, and this is part of the cost as well. So I hope I reply. And if needed, I can also answer by email, so don't hesitate to ask more if needed.
May I ask you a very short question, Laura? Yes. Because I've noticed in the images that when you saw the colored modules, there's no interconnection of the modules. So these are back contact interconnections, or how do you hide interconnections?
So no, it's not back contact. So sometimes it's back contacted with sun power cells, for example. But otherwise, what we do is that we have to put black bus bars. And this is important. Otherwise, you would see the bus bar behind. So module manufacturer in the BIPV field, they usually do black bus bars. So it's how we proceed.
But at the end, they are invisible. You don't notice that.
Yes, you don't notice because you have a black background, black cells with black bus bar, and you don't notice anything.
Okay, you have no contrast with the cell. That's it. Okay.
No.
Okay, thank you.
Thank you, Laura Emmanuel. And I actually had one question also for maybe for you and also for Jose, but I know that he has to leave now. So for BIPV Boost, I think that both your projects, you are insisting on the aspect of cost efficiency for BIPV to deploy this market. And I think you saw in the presentation from PV Sites, our company R2M, we are the reseller of Onyx Solar in France and Italy. And so personally, I'm taking care of the French market. And what I see from the market perspective for BIPV is that so far it's not so much the cost, the barrier, but I would say it's much more the certification aspect, the regulation aspect, which is a very strong market barrier. Basically, the market players, they are not familiar, with these new kind of components, even the ones which are very basic. I'm not talking of the very, very advanced components that you are working on in some of these projects. And it's already very complex for them to handle that. And I wanted to know if this is also the feeling you get from the stakeholders in your projects, because this is maybe something which is French specific, I would say.
Yes, you are completely right. And so this question of cost is really at the center of the project, because also the call of the Europe was really focused on this cost reduction. But very quickly, I think it was the same discussion between all the projects related to this cost, was to say, well, it's not only a costly question, because we have made also interviews in Switzerland, and it's probably like on the French market. People are ready to pay more to have a well-integrated installation. And in some case, like we have many cities here where you just cannot install black modules. You need to find a way to integrate it because of heritage specification. And therefore, the question is not firstly the cost. As I think the first question is, of course, it depends then if you are an architect or if you are the building companies, but the aesthetic is very important, and all the normative aspects are very important. Administration, the number of documents you have to fill to be able to install 10 panels on your roof. I mean, many people say just, well, I'm not able to do that. And so there is a long way, there is a long improvement that we can do also in all this process. And at the end, it's a question also of communication, of education, on making all these, of bringing a methodology which seems simpler. But when we talk about photovoltaics, it is something simple. It's not something difficult. And it is a bit, yes, it is a bit also what we conclude now, and we are just at the middle of the project. It's not a question of technology. It's not a question of know-how. It's a question of communicating well about what we can do, showing example, and then just align also some normative aspects, which sometimes it's hard to see really the sense they have, but just to try to simplify all that to be able to push this implementation of photovoltaics. And that it is also a political question, because all these barriers are also politics. So if we really want to go for PV implementation, we just simplify process, we adapt norms quickly, because it's not something which is so complicated. At the end, it's just a glass panel, which is producing electricity, but it's a glass panel. It's nothing else. So yes, there is a lot of different level of strats that can be improved.
All right. Thanks very much, Laura.
May I comment something? In principle, I also agree, but I think there are some. You are right that cost is not the main issue, but I think this is because also the BIPV market at this moment is restricted to the prestige buildings. If we want to move to the 100% buildings, normal buildings for residential areas and so on, cost will become a very important issue, because when we speak about our own houses, if we think about replacing the facade, or we think about painting the facade and renovating and all these kind of things, then cost becomes one of the main issues that people is aware. And I think this is one of the potential barriers that we need to address at some moment for making really a mass deployment, because the problem is that we limit to prestige buildings, we will never go to mass deployment. We will be only restricted to very specific applications. And that goes to we need the regulation and we need policies. That's exactly. I think that's really important.
Yeah, and this goes in line also with trying to make standard on the size to be able to increase also the volume of production. If each project on the building has to be customized completely, of course it will stay expensive, and it will be for more prestige buildings. So this is also the work, is how to bring PV more in, to democratize the access of PV.
Easy modularization and prefabricated elements, all these kind of things are really important. Regis, I don't know if you wanted any other question to add, or? We
no,
are
I think
late in relation to schedule.
I think we managed all the questions so far. And again, so first of all, we will share this recording online. So that's an opportunity for people to, I would say, watch again the presentations and perhaps ask more questions after the event. Yeah, and again, we of course will share contact details of everyone, including the attendees with the speakers, so that you can continue discussing all of that offline.
Okay, so maybe we're moving to the closing of the session, I guess. So thank you very much to everyone. I think it has been a very, very interesting session. Very dense, has a lot of information. I think that's very good because there is really this is a lot of issues that have to be developed. I think BIPV is a reality now. It's still a niche thing, a minority thing. We have to do the deployment. I think that this will take some time, but we have begun the work. So thank you very much for everyone. I don't know, Regis, if you want to say some other thing for closure.
No, I think it's all good, and thanks very much to you, Alejandro, for chairing the session and organizing everything. It was really, really interesting, and thanks to all the speakers.
Thank you very much to everyone.
Thank you.
Thanks a lot. Thank you. Bye.
Bye-bye.
Bye-bye. Take care all.